I'd like to share a stream I did a few weeks ago about learning WebGPU. On the stream, I'm learning WebGPU for the first time, and I don't really know anything about WebGPU other than what I've read and what I know about WebGL. So if you'd like to watch that with me and learn with me as I struggle, come and check it out. WebGPU was just released by Chrome, and we've been waiting for it for a while. I stream every Sunday at twitch.tv/eonerheim. I got lots of cool stuff on GitHub. A lot of it's game related, and I make a 2D game engine for the web written in TypeScript called Excalibur.js. Huge thanks to all my sponsors and patrons. And if you'd like to sponsor me or be a patron, I'd be much appreciated, and you help me do this content. And with that, let's get into the stream. All right. Well, today I'm going to struggle through some WebGPU. Chrome has finally shipped WebGPU, and it's pretty exciting. We have dealt with WebGL and WebGL 2 for a little while. We've been waiting for WebGPU for a good long while. It's supposed to bring a lot of additional performance to graphics pipelining. It's inspired a lot by Vulkan and Metal, but as far as I know, it's a little better than Vulkan in terms of amount of boilerplate that you need to get something going. The classic punchline is that you need several thousand lines of code to get the hello triangle going. So WebGPU though is a lot less verbose than that, but it's still more verbose than WebGL. So hopefully we can struggle through. One cool thing about WebGPU is that it abstracts the graphics pipeline a little more, or a little less, is what I meant to say. You get a little more control over the graphics hardware. And in fact, they even have a facility for doing compute shaders. So you can do compute programs on the GPU now instead of having to do like wild things like in WebGL where you might encode your problem into a texture, and then in order to read out the results of your compute shader, you had to read it out of a texture, which is kind of a hack. So WebGPU comes with that API as well. So, all right, let's dig into it. So this week, kind of surprisingly, we got Chrome delivering WebGPU in Chrome 1.13, which is pretty exciting. This is actually going to be a huge boon for like performance, because right now in Chrome you have to bounce through a translation layer for WebGL in order to like convert WebGL commands into like either DirectX or Vulkan commands. So these are a lot closer to those native commands. So the translation layer is a lot thinner, so that should improve performance as well. Yeah, the can I use page. Can I use WebGPU? You can on Chrome 1.13, which is the beta channel. So it's like almost in Chrome. This is I'm using Chrome Canary here in this setup, but it's almost out for everyone. So I have a great video too. If you want to check out a YouTube video after this to kind of, it's like a 2-hour long video here. I watched on a flight, but I'll post this in the chat. But it's a great video if you want to go over that later. But let's take a look. There's also a fantastic website called WebGPU Fundamentals. So I'm going to start there, I think, to learn how to do WebGPU. Um, uh, in the WebGL world, a lot of it is you're poking at the WebGL, OpenGL state machine that exists globally, and then there's kind of this implicit screen texture that always exists. So when you draw, it just draws there. But WebGPU, that doesn't exist. So you need to set up a lot more of those things by hand, as far as I know. So there's also a different shading language compared to WebGL. So there's GLSL, which many of us know and love, is kind of a C-like language. WGSL, I think pronounced Wigzel, is kind of a different looking language, and I'm not sure what it's inspired by. Maybe it's inspired by Swift or Rust. Maybe it looks like Rust. Who knows? But it definitely doesn't look like GLSL. Well, it looks close. It's close. It's nearby. But yeah, let's just get started. I have a code window here, so let's switch over to coding, and let me open this up. And this is a completely empty coding window. So let me get that going. There we are. So let's just get started. I know we're going to need some HTML. So let's just get that rolling. Running WebGPU. So I'll just throw down some HTML. Why not? I like TypeScript, so maybe we can use TypeScript. Maybe that's a bad idea. Let's try it. So I'm doing npm install here. Npm install save dev, save exact. So we'll go ahead and install TypeScript. And that's just something I like. You don't have to use TypeScript. You don't like it. And that is okay. I am a big fan of Parcel. It is like magic. So let's grab Parcel. And Parcel is a kind of a magical all-in-one build bundler tool. So it'll build our TypeScript, run our HTML, and get us rolling real fast. So we got Parcel. Let's add a get ignore because we have some node modules here. I don't want to check those in by mistake. Node modules. You know, it might also help is if I make this Git repository just so to save our changes as we go. And I can share this code with y'all later. All right, so we have that set up. Let's initialize a new TypeScript repository. There we go. We got TypeScript, and this is just the default thing that falls out of TypeScript init. So that command I ran was tsc init. So that's just a quick way to do that. I'm just going to add a main. We're just going to call this hello web GPU. We're just going to make sure that this works out okay. We're going to wire this up to our let's see, I always forget what this is like. needs to be a module of some kind. Let me double check. I think it's type module. Okay, yeah. Forget that. All right, so let's set up parcel. Let's go ahead and run parcel here. Status scripts. Parcel. I always forget the command for this. It's parcel serve. All right, let's try that out. We'll run the npm command, npm run start. See how it goes. Oh, I already have that port in use, but that's okay. We'll just go over here. Make sure it works. Huzzah. There we go. Parcel's running. Hello, WebGPU. Yay. Very exciting. All right. So let's go back to WebGPU fundamentals and start here. So now that we have our project kind of running and building locally here, let's look at what we need to do code-wise. Let's see. Well, it expects we know about JavaScript. Well, that's important. So I guess mapping, destructuring, spreading, async, await, ES6 modules. Cool. If you already know WebGL, read this. Cool. I theoretically know WebGL, but maybe I don't. Let's look at that. Let's see what. Oh, cool. That's kind of what are the big differences? Oh, this is interesting. So this is the what I was talking about earlier. This is a comparison of the shading languages. So in WebGL, you have GLSL, kind of a C-like language with kind of special variables. GL position is like a special variable that you assign to output the position out of your vertex shader, and then frag color, GL frag color is like a special global that you output to in your fragment shader. You can think of that as like, this is a piece of geometry and this is a pixel on the screen. That's not quite right, but you can think of it that way. And here is Wigzil. Looks like you can define structs. Looks like you can specify uniforms, and it looks like there's this decorator here to tell us where this is going to live. So at position 0, binding 0. Here's another struct here that has different locations. So we have a input, so we have position, normal, texture coordinate. It looks like, again, some decorators here that tell us a little bit about their layout. Looks like we can have both a fragment and a vertex shader in the same file, so that's interesting. That's kind of nice. So we'll probably play with that. It's nice to not have two separate strings that you have to deal with, so that'll be interesting. Okay, so it basically looks the same, just the syntax is a little funnier. Maybe Rustish, Rust-like, Rust adjacent. All right, so biggest difference is WebGL is stateful, so that global state machine I was talking about, and WebGPU is not. That's actually, I think that's a great thing. So that'll be nice. So there's no global state. So you have to do all kinds of things to set up the state machine in WebGL, like bind and enable. WebGPU, you create pipelines and you run the pipelines. Sounds pretty straightforward to me. The other difference here is it's lower level. I think we were saying that earlier. Okay. Well, I think that is a good gist. Let's get into some code. All right, getting started. All it does is run 3 types of functions: vertex shaders, fragment shaders, and compute shaders. Well, I'm not going to talk about computer shaders today, so we're going to do vertex shaders and fragment shaders. Vertex shader takes and computes vertices and gives us the position. And a fragment shader computes colors. And then we interpolate between colors. Cool. And we don't care about compute shaders. If you think about it, these are similar to an array for each in a map. So we're going to pass it a bunch of vertices. We're going to run all of this stuff, and then it's going to do all of this thing on the GPU. So let's look at this diagram. Here's a simplified diagram of WebGPU to draw triangles. All right, so let's take a look here. So we're going to set up a render pass. So that's that data structure that we want to send into WebGPU, and or that pipeline, and it's just going to take all of the information we need. So it's going to have buffer, and buffer is just like an array of data, and it might be, usually it's vertices. So you can think of buffers as like a big array of vertices, and then you tell it, oh, this grouping means this, this grouping of numbers means X, Y, and Z, or this grouping number means X, Y, Z, and something else, or whatever you want it to be. Usually it's vertices, can be anything you want. Might be normals, might be vectors, whatever you want. Textures, I don't know what a texture view is, but we'll find out. I imagine it's maybe a slice of a texture, if I were to guess. A bind group looks like it holds all of the information about various things that we might have bound in the old world of WebGL. So we have a uniform buffer. A uniform is a fancy word, again, for things that don't change as you're processing a screen. So uniform, it means it's uniform for the entire screen. So you can think of it as like that. Versus an attribute, which changes over the pass of a screen. Okay, so we have all the state that we wrap up into a pipeline or a render pass. I'm trying to figure out which is the top level piece of data structure. Might be a pipeline, might be render pass. Not quite sure. Looks like maybe pipeline. So you heard me talk about attributes and uniforms. So an attribute, things that change while you're calculating the screen to draw. And a lot of that is geometry. So that's like vertex buffers. So the geometry changes over time. Other things might change over time, like colors and stuff like that. So those would all be attributes. Uniforms are the same for every pixel. So you can think of that. And then we have our vertex shader, fragment shader, and that all feeds into a render pass. What is a render pass? I don't know. We'll find out. Looks like there's different color attachments. If I had to guess, this is just how do you output to output texture, and it looks like canvas ? Is like the screen is a possible attachment. So you can have a color attachment which is the screen, and you might have an attachment here which is a depth buffer. If I were to guess, knowing nothing about WebGPU, I would guess that is the case here. And you might use a depth buffer, like if you're doing a depth buffer in WebGL, that's how you know if something is above or behind something else. So like if you're doing, you're ordering stuff. A lot of the time, I know a lot of folks just wind up ordering geometry on the CPU because there's problems with doing depth on the GPU sometimes, depending on your problem. So, like me, I order on the CPU for our game engine, Excalibur, because of transparency. Because transparency is real pain to get right. And a lot of times you just have to draw in the right order to get transparency to work right. Okay, let me read the text. There is a pipeline. It contains the vertex shader and fragment shader. And I'm not doing computer shaders, so that's fine. Okay, so the pipeline, vertex shader, and fragment shader. Shaders reference resources indirectly through bind groups. Okay, that's cool. All right. And that was that bind group. So we got a bunch of resources here. So we got buffers and textures and samplers and uniforms. Okay, I think I'm following. Let's see. Pipelines define attributes and reference buffers indirectly through internal state. Okay, so that pipeline, it sounds like, is that top level object that we're going to build. Attributes pull data out of buffers and feed them into the vertex shader. Cool, that's tracking with WebGL. Remember what I was talking about, like, a vertex buffer might be a piece of geometry. An attribute is just, this vertice in the vertex buffer. And then, as we're chunking through, it'll read each vertex that it needs to read. Fragment shader writes to textures indirectly through render pass description. So I guessed, without reading the text, I think pretty closely what it does. So we can decide, okay, with the pipeline, we decide how we're going to process data. And then the render pass description tells us how's it going to land. So is it going to land in a texture, potentially the screen? Is it land in a depth buffer? Looks like there's multiple ways we could do this. Cool. That makes sense to me. I think. We'll find out. All right. Let's see. To execute shaders on the GPU, you need to create all the resources and set up in state. So there's a lot of boilerplate is what I'm reading here. It's pretty straightforward, but we need to do a lot of stuff. So in order to draw something, we need to create a command buffer. What is a command buffer? Well, if it's like any other buffer, it's a list of commands, I guess. Let's see. A command buffer here has a few things. So looks like in this command buffer, we have render pass, set pipeline, vertex buffer is a vertex buffer, index buffer. We can talk about index buffers later, but it's kind of like a way of trying to avoid repeating yourself. And then we have different bind groups, we draw, and then we end. Okay, so that's not too bad. So looking at this diagram, we have that pipeline we were talking about, which is like the how. Like here's all my data and resources that I need. And then I have a render pass, which tells me how it lands. Okay, so let's take a look here. So I am going to create a command encoder, and I'm going to go ahead and set all of my information here. So I have to create a pipeline. It looks like I add all my stuff, I draw, and then I end. Okay. Seems okay. And then we just get a reusable command buffer, which is kind of neat. So like if you have different ways of drawing things, you don't have to repeat this code. It looks like you can just submit it. Well, maybe you do have to repeat this code. That'll be something interesting. Ideally, I would like to not repeat this code, right? Because if I have a command buffer, that leads me to believe that I can just fire this at the GPU to draw stuff. That seems like what it's doing. We'll find out. Okay. All right, I think I am understanding the concept. And I'll repeat it one more time. Uh, we need to set up just an object like that is an object that contains all of our state. Um, and this is different from WebGL in that WebGL holds on to global state. So that's kind of nice. So we can set up an object instead of having to poke the global state over and over. Uh, so we'll set up our pipeline and then we'll set up our render pass and tell it where to land. Okay. That seems okay. And it looks like we do that with a command buffer. Oh, and this is pseudocode. Okay. So that helps. All right. All right. So WebGPU can draw triangles to textures. Yeah, so we're gonna draw some geometry to textures, and our texture in this case is we want it to land on the canvas. So awesome. Well, I suppose we should get started. So we need to make a canvas. Put some JavaScript in there. Looks like we request a device. I'm assuming that's the GPU. We have this adapter and device. There's probably a reason for that. And once we do that, we configure our context. And then are we off to the races? We have a context that we configure. We have, okay, there's a bunch of shader nonsense. All right, so it looks like we configure a context, build up some shaders, and then we can submit to the device, is what I'm reading here. Maybe I am understanding it, maybe I am not. Device, encoder, we have a render path, set a pipeline, yada, yada, yada. Render. Okay. Well, let's see if we can do that without copy pasting too much code. So let's switch over to code now. And let's take a look. All right. Cool. So let's throw a canvas down here. I'm going to make a game sometime soon with our WebGPU. Let's go over here. Let's set up our main. So define the main and call it. So we need to grab the adapter. What is the adapter? I want to know. GPU. All right. So let's find out what that is. All right, so I want to understand what the difference here is between the adapter and the device is. Okay, is this hanging off Navigator? Navigator. GPU. So I don't have types. Let's see where I can get those WebGPU types, because I would like to have types. TypeScript, WebGPU. I would like WebGPU types, please. How does one get WebGPU types? I would like them because I don't want my red squigglies. Looks like I can, there's a package out there called GPU web/types. Cool. Looks like it was last updated a month ago, so maybe this is right. Cool. Let me switch over to the browser here and let's show you what I'm looking at. I'll paste this in the chat. So let's try this. So sure, let's copy paste commands. Why not? Let's look at this package here. Looks like it's pretty popular. Passes the sniff test. All right, works for me. All right, so let's go install that. So if I am understanding the documentation, all we need to do is throw that into our type roots. So it looks like they have a code snippet here. I'll just throw that down. Theoretically, I will have GPU types. Haha, I do. That's nice. I love it when stuff works the first time. That is nice. All right. Let's see if we can understand what... Okay, let's see if we can understand what an adapter is. Let's look at MDN. MDN has a lot of good stuff. WebGPU. And we'll switch my screen over to the browser so you can see what I'm doing. Okay, a WebGPU adapter represents a physical GPU and driver available to the underlying system. Okay, cool. So the adapter is the abstraction over the device. Okay, so when we grab the adapter, we check if we got one. Okay, let me scroll back up here. And then, okay, and then we request the device out of the adapter. Okay, cool. Following so far, I just want to make sure I understand this as I'm going through it, not just pasting it. Adapter. Oh, it's so nice to have types. Look at that. Okay, request device. What did request a device from the adapter? That's a very tautological way of doing it. Okay, so if we don't have a device, something has gone terribly wrong. Let's just throw. No WebGPU. All right. And I'll be nice and I'll wrap it in there and not just throw a string. Okay, so let's see how that looks in our browser. Make sure it's building. Cool. Refresh. Cool. Doesn't look like it bombed. Let's see how we are looking. My source maps aren't working. Source maps detected. Well, they are. It's not. They're not working. Do I need to do source maps here? make source maps work. Oh, well, I guess we're going to live with no source maps. Oh, here we go. Oh, sweet. We can get at... for some reason, they're not showing up here on the left, but I can Control P for them. All right, well, we'll go with that. All right, so let's just refresh this, make sure it's actually running. Cool, we're going to get at the GPU. We got our adapter. Oh, features. Size 6 is a feature. Fallback adapter, false, limits. Oh, this is interesting. These are all the limits that we have. Let's take a look at those. Okay, we got a bunch of maximums. Max buffer size, that's going to be interesting. So especially if you're writing if you're building a batch renderer, that's useful. Okay, so we have a bunch of maximums. Max texture. That's useful to know. That's very nice. Okay, so we have a bunch of maximums. Let's see what we have out of a device here. We have features again. We have limits again. Was I looking at the wrong thing before? That's an adapter. A device. Okay, what's different? Okay, so they both have their limits on them, which is interesting. There's lost, whether or not it's lost. I imagine that's if the device is pulled from you. I wonder if that's like WebGL when you lose the context. We have a queue. I imagine that's where we submit our commands. We submit them to the queue, I bet. Cool. All right, so that looks like it's working. All right. Cool. All right, so we did all that. All right. We're gonna create our canvas. We're gonna grab our canvas, create a WebGPU context. This is how we get the texture. Okay, so, all right, so this is, okay. All that we really do when we do this is we're getting a texture for WebGPU to target. So that's the whole point of this. Okay, so let's do that. Get element by ID. I think I called it game. Yeah. Okay, it's upset about something. Let's see what it is upset about. Is it because it could be null? Yeah. I promise, I solemnly swear that it will not be null. So what I'm doing here is I'm casting it instead of as the HTML or null. I'm saying, I know better. It's going to be a canvas element, I promise. Not generally a great idea, but it'll work for now. Let's see. Make sure that everything is going well here on the stream. I haven't looked at it in a little while. Cool. At least 3 people watching. Exciting. Well, I hope you're enjoying the sultry sounds of WebGPU. All right, so let's see. We need to grab our presentation format. And if I remember correctly, this is just a thing that your platform prefers. So this is like 2 different ways of organizing data. So it might be, this, or it might be this. And one of them is going to be faster for your platform over another. So that's what this is for. So you're saying, hey, what does my platform prefer? Grab that. And we're going to use that. And I guess we have to configure it because maybe you, like, in the name of maximum customizability, you might want to use a specific format, even if it's not optimal. Maybe you have maybe you have some code that depends on the particular format, I imagine. So this did a little trick for us here. So instead of us having to type the key twice, if the key is the same name, you can omit it. So that's all that was. So configures the context for this canvas. Clears the drawing buffer to transplant back. Okay. So if I understand this right, the reason we do this is so that we have a texture. So we basically have configured a texture that exists that we can run the WebGPU attachment. Run WebGPU to land on the attachment. Let's go back to this diagram. So we can just get it to the screen. So if I look at the browser, we've configured that device, that canvas, so that we have this. So we have a place for the render paths to land. So cool. I think that makes sense. Okay, so what's next? We've got a device configured. We probably need so we either need one thing. We need a few things. We need some shaders. So we need a fragment shader, and we need a vertex shader. We need to configure a render pipeline. So let me switch back to the browser here. So we need to configure this pipeline. We need this, and we need this. Okay, so let's do that. Let's do a pipeline. How do we do a pipeline? So we can create a pipeline with the device create and render pipeline. So let's do that. So const pipeline equals device create render pipeline. Looks like there's different ways to do it. All right, descriptor. So we have this huge option bag available to us. Oh, it looks like we can label it. Sweet. Our sick triangle rendering. Layout. We give it a layout, and then we give it a vertex shader. Vertex. I'm just gonna give it the wrong thing here. We're gonna give it a vertex shader, and then we're gonna give it a fragment shader. There's some configuration there. Okay. Slick. All right. So we can give it a layout. So layout is, I'm assuming, the attribute layout. So there's an auto, which reading the documentation says when we set the layout to auto, which means ask WebGPU to derive the layout of the data from the shaders. Oh, that I bet you is this business right here, where we throw the decorators in to our shader, and it'll figure out the position in our buffers of where all of these things are. So if we have a vec4, the first position is it's going to have 4 floats, and that's going to be, X, Y, Z, Z, W. Okay. All right. I kind of like that. That kind of rocks. That kind of rules. Okay. So auto it is. I like auto. All right. And so then we need to define a vertex shader. So I'm just going to leave this broken. And let's create our vertex shader. Remember, vertex shader is just a program that runs for every vertice that you have. And then a fragment shader takes the output of your vertex shader and then runs for every pixel. Cool. Let's create a shader. Let's see, shader equals, so we use device. What do we got here? Create, so I want to create a shader. Create shader module. What is a shader module? Let's look at WebGPU on MDN. Shader module. Let's try again. Oh, I probably need to specify WebGPU. Cool. All right. A container for WGSOL shader code that can be submitted to the pipeline. Awesome. So that's what we want. So we need to create a shader module. And let's take a look here. Code shaders. That's not super helpful. Where does the shaders come from? Oh, it's just there. Oh, okay. So we just literally... Okay. We literally just throw the code in there. Okay, code. And then we just dump code in there, I guess. Works for me. Is there any other properties in here in this option bag? I am like morbidly curious here. Let's see. Create shader module descriptor. Ooh, you can have a source map. Okay, so this is the WGSOL. This is the code. You can have a source map. That is cool. Hints. You have to find maps in Azure Point. Interesting. So you can light up some maybe interesting features in your graphics hardware with hints. And then source map might be useful if you are compiling. I'm not sure where I'd use this, but maybe if you need to, I don't know, find the original source like you do in JavaScript. That's very interesting. Okay, cool. So the only thing we really need to worry about is code. All right, so now we need to learn how to write WGSOL because I've never done that before. Let's see, how do we write WGSOL? Should we just steal what they have in this WebGPU fundamentals? I think the answer is yes. Let's steal it and then see if we understand it as we go. Okay, so, oh, there's this label thing. Can we label everything? Oh my God, let's label everything. Shader code. That's gonna be awesome. Okay, so let's take a look here. We have a vertex. So it looks like a vertex attribute. So it's a function vs. I don't like that. So let's call it fn. I'm assuming is for function. Let's call it vertex. And there's some parameters here. So let's start with the basics here. Vertex. And let's do the same for the fragment. Work our way in. That's not how you spell fragment. Okay, so we got a vertex and fragment. My syntax is wrong for sure. Let's see here. Vertex and fragment. We need looks like we have this built-in vertex index. Built-in vertex index. What is that? Function called VS is declared with vertex. Okay, so I think we know that. We know that the at vertex and at fragment tell us which function is which. Vertex index is a U32 unsigned 32-bit integer. Okay, what is this built-in business? I don't know what that is. Doesn't tell me what that is. Huh. Doesn't tell me what that is. Let's see if we can figure that out. Let's go to this language. Built-in. What is built-in? Frag is built-in. Okay, I'm putting it together. Is built-in like special built-in features of WebGL versus attributes? Because I saw. Okay, I'm thinking that's the case. I'm wondering if built-ins are... Okay, here we go. Certain functions are pre-declared provided by the implementation, therefore always available to use in WGL. They're called built-ins. Okay. So that's just a thing that exists that we can just conjure and use whenever. So that's what a built-in is. It just says, okay, WebGPU, you can always ask for these things. You can always ask for the vertex instance, the frag depth, the sample mask, yada, yada, yada. And you ask for it with built-in. Okay, that makes more sense. All right, so that's what built-in is. So built-in is just saying, hey, there's these built-in attributes in WebGPU, and I can just conjure them out of the ether as long as I add the at built-in, and that'll populate my vertex index here. Okay, and then I'm assuming, okay, but the output is also a built-in. Is that like saying this is the built-in, okay, I'm assigning into the built-in position? Is that what that is? That's what it looks like. Vertex output, built-in position. Well, I'll be darned. I bet you that's it. So like in GLSL, there's a special, let's see if I can find it. There's a special like variable that you need to assign your final position to called GL_position. I bet you that's what this is. Okay, so I'm following. So it looks like built-ins can be inputs and outputs, depending on what they are. And in this case, I want a vertex index, and I want to conjure it out of the ether. And then I want to assign whatever I figure out to the output. Okay. And it looks like this is just the input, is a built-in vertex index. So I'm assuming vertex index is given all of the vertices that we submitted to the GPU. This is just the number that it's assigning to it. Okay. All right, let's hop back over the code here and work through this. Okay, so we have our vertex function here. We have that built-in that we're just calling from the ether. Very nice. Then we have this funky arrow syntax. We need to grab the built-in for where we're landing, which is we're doing a calculation and producing a point, a vec4. So vec4 is just 4 floats. A vec4f is just 4 floats. So we have a x, y, z, w. So let's go ahead and do that. So we need to return. Let me just return a vec4 right now, and we'll just return, like, I don't know. Let's just return 0.5, 0, 0. And then in their example, they have a w of, it's x, y, z, w. And w is used mostly for like perspective stuff. So you can mostly ignore it. Okay, cool. And if you have any questions, feel free to hit up the chat. Or if you think I got something wrong, feel free to comment in the chat and we'll take a look at it. All right. So we have I think we figured out vertex shaders. We have a very, very, very simple vertex shader. This probably needs to be commented. Otherwise we'll be sad later. We have very simple vertex shader. Now let's move to the fragment. Let me switch back over to their example and let's see if we can understand it. Oop, wrong camera. So taking a look at their example here, what are we looking at? So we understand this. We know that we can say, okay, this is the vertex one, this is the fragment one. This has no inputs, has an output to location 0. Location 0. I don't understand that. Let's see if we can. Let's look at location 0 here. Where is our spec? Okay, let's look at what is location 0. What does that mean? So in this example, they're also outputting to location 0. I would like to understand what location 0 means in this context. Location 0 example of entry point. Okay, the set of functions in the shader. Okay. Targets of the function will be applied. Blah, blah, blah. I don't understand location 0. If a function does not have a return type, then the return statement is optional. If the return statement is provided for a function, it must not supply a value, otherwise the expression must be present. Return value. Okay. Yeah, okay, well that's returns. Entry point declaration, use defined function shader language. When configuring a pipeline, WebGPU, the entry point's function name maps to the entry point attribute of the WebGL. GPU programmable stage object. Entry point's formal parameters denote the stage's shader inputs, and an entry point's return value, if specified, denotes the shader stage outputs. Okay, here we go. IO attributes are used to establish an object as a shader stage input or output. Okay, so as we talked about earlier, built-ins are just built into WebGPU, and we can use them as outputs depending on what they are, or inputs. But it looks like we can also land attributes, or land output into locations. Must only apply. Specifies user. Okay. Interesting. So, location 0. I still don't quite understand that. If someone knows in the chat, that would be really great. I don't understand the significance of location 0. All I can tell is that it seems to be what they do. Yeah, they didn't explain location 0. I am not sure exactly what that means. Location. Specifies a part of the user-defined IO entry point. Can't be used in a compute shader. Okay. Each input-output location can store a value up to 16 bytes in size. Well, that's good because we want to store a color, theoretically, right? Because the output of a fragment shader is a color. Each user... No, the location distinct location. Okay, no additional rule is required to prevent location overlap within an entry's outputs. Well, here's what I'm gonna guess. I think it's totally arbitrary, and here's why I think that. I think it's completely arbitrary because if we go back to this diagram, there's color attachment 0, 1, yada yada yada. I wonder if we wire up to a location later on, and whatever we pick is whatever we pick. That's gonna be my guess. So I'm gonna go on blind faith on that one. We're gonna go on blind faith with location 0. But my guess is that it's just a holding zone for a 16 byte value, up to 16 bytes. And that's fine for us because we're gonna hold a color. But we might have to look at that a little bit later because I don't necessarily understand that, but I'm guessing right now that is completely arbitrary and they just picked 0 out of convention because why not? And we're going to wire up that later because we're writing to location 0. Cool. So you can IO to these things. So we saw this built-in and we saw location, and we can IO to them. 0 seems like it's completely arbitrary, so I'm gonna go with the flow. And so this is so we're writing out a color. So we're making a super simple fragment shader. So every pixel is going to be red. So this is RGB. Alpha. So alpha of 1. So opaque. All right. All right. So now that we got our shader, let's go back to our. So we just did that in one go. So we don't need to. So that was both our vertex and fragment. Okay. So now we need to figure out how to wire up this stuff in a render pipeline. So we have a vertex, we have a shader. So it says we need to wire it up like this. So there's a module, which is a shader module. I wish they would have just called that shader. I just feel like that's more clear. Then we say the entry point. Okay, that's easy enough. It kind of sucks that we have to say the entry point because it has a attribute on it. Why do we have to say the entry point? I wish it didn't need that. Do we have anything else in here that we need? Let's go look at the type definition. Vertex. Looks like we can give it buffers, we give it a shader, we give it an entry point, and any constants that we care about, which are numbers. We can give it the numbers. Okay. That seems like it tracks, and fragment I think will be the same. Entry point, fragment. And we need one more thing. What do we need? Let's go look at the types. What do we need for fragment? Fragment. Targets looks like the thing I'm missing, but let's keep digging. So yeah, module, entry point, and constants are the same for vertex. So targets is what I need. So I need a target of, so I need a list of some color target state. And looks like we must say the format, and then some optionally we can talk about blending, or there's some flags, which are probably bitwise flags. So we don't care about that. So we just care about the targets. So let's go back and do that. Targets. And we needed format. Let's format this so it looks pretty. And then we needed a format. It looks like we have a presentation format, and that's just the preferred format that we got for our platform earlier on. Okay, cool. We have a pipeline, folks. We have a pipeline. Does it draw anything yet? No, but we have it. All right, so quick review. We got the adapter, which is the abstraction over the device and driver. We got the specific device, tossed an error if we couldn't get at it. We got the canvas, configured the canvas context. This is to give us a texture that we can draw to later with WebGPU. We created a pipeline, and remember that pipeline is going to run and output given a render pass output to a texture, which is that canvas context that we want, and then that pipeline inside of it has a shader. Cool. I think I'm following. I think I'm understanding. Neat. Okay, so now we need to figure out how to render. How do we render? We need to create okay, let's look at this. Let's look at this picture again. Let me pull up the picture so that we can orient ourselves, because we've done quite a bit of the setup. There's a lot of setup still. It's not as bad as Vulkan, but there's still quite a bit of setup here. So what have we accomplished? We've got this pipeline. We've got a vertex shader and a fragment shader. We don't really have any attributes right now because we're hard coding stuff. So we'll probably get that in later. We're not drawing any pictures yet, so we don't have any of this business yet. So we have a really simple pipeline. So it looks like the next thing in our list here is a render pass so that we can write to the canvas. Okay, so let's let's look at a render pass. Let's go MDN WebGPU render pass. Render pass encoder, maybe. Encodes commands related to controlling the vertex and fragment stages issued by a pipeline. It forms part of the overall encoding of a GPU command encoder. Okay. Let's see if there's an example on here. So we have our pipeline. We've already set that up. Looks like we need to create a command encoder, and then we're going to do a render pass. And then we're gonna, looks like we're near the end. Okay, cool. Let's set that up. Let's go back to coding. All right, so we need a command encoder. Command encoder, device, create command encoder. This is the thing that's going to run our list of commands. And then we need to render pass. We need to create our render pass from the command encoder, begin render pass. And then we have to give it some options. So what do we give it? Let's look at the types. Look at the types. When in doubt, look at the types. All right. Color attachments is required. Depth, occlusion, timestamp, max draw, those are all optional. So it looks like we need color, and then we can give it a label. Let's give it a label. Let's call it my awesome render pass. I imagine these labels, I think I saw it's super useful for debugging. When something fails, you get like a human readable error with your label. So if, you know, one of the biggest problems with like WebGPU, or excuse me, WebGL is like when something would bomb, it would just not draw and you would be sad because you'd be like, why it no work? And then you would just spend a day flipping bits until something drew to the screen, and you'd be very sad. Okay, so let's see what's involved here in color attachments. What is a color attachment? So we need a list of color attachments. We got a view. Okay, so this is our output. So this needs to be our canvas, if I am not mistaken. So that's required. And then there's a few others, and there's a few other things that are required. There's load op, indicates the load operation to perform. It's recommended to prefer clearing. Load op clear. Well, okay, we can do that. Store operation to perform on the attachment after executing the render pass. Okay, what is the store op? We can either store or discard. I'm gonna guess that we want store. They don't tell us what they mean, but I'm gonna guess that we want to store our value to the canvas texture. Okay, so that, I think that tracks for me. So this is the part where we're wiring up to that canvas context that we set up before. So we configured this canvas context here so that we could have a texture to draw to, and that's what this color attachment is. It's our target. So clear value we said, or excuse me, load op we said was clear, and then store op we said we were going to do load, or not store. Store. Okay, and then view is our canvas. So context, what can we do here? This looks like what we want, right? This is their canvas context that we got here. Canvas context.get current texture is not the right thing. What do we need? This is a rough error. I need a view. Okay, it says view GPU texture. Okay, here we go. Property view. Texture view. I need a GPU texture view. Okay, so maybe there's a create view. I don't think that's what I want. Is it? Is that the only thing that's a view on here? Do I just need to create a view? All right. Okay, let's look at MDN. Okay, that's what they do. Okay, that's what MDN does. And I am missing something. What am I missing? Or undefined. Okay, so I solemnly swear that this is not undefined. So this is generally a bad idea, but I am saying that, okay, I'm saying that this is definitely defined to TypeScript. So with a bang. Okay. Slick. Okay, so we got a render pass. What do we do with this? Let's take a look back over at MDN. So we have this render pass with begin render pass, and then we set a pipeline. We set a vertex buffer. We draw a certain number of vertices, and then we end our render pass. So we know that we have a pipeline, so we already defined our pipeline. So let's go ahead and set our pipeline, which we got here. We don't have a vertex buffer, so we don't need to do that. Let me switch back over to coding here. So we set our pipeline. We don't have a vertex buffer. I'll write it in there just because I think that's where I'm going to go next. You know, some vertex buffer TBD. So we're going to go there next, but I'm not going to put it in there. I know we're going to draw a triangle, so I'm going to draw, it's the number of vertices to draw. So I know I'm going to draw 3. So we're going to draw 3 vertices, and then render pass end. So we're, okay, so this is, we've captured our command buffer. So that's what this is. We've captured all of our rendering commands. And then theoretically, we can submit that to what's command encoder? Schedules. Okay. I just wrote this code without really understanding it. So let's take a look here. Command encoder finish completes recording of the command sequence, returns the command. Okay, I thought that's what this did. Render pass encoder end completes recording of render pass command sequence. Okay. Then we have a command encoder finish completes recording of the command's sequence and returns a corresponding command buffer descriptor. Yeah, that's interesting. That just looks like what we wrap up. It like wraps up the package so that it's ready to go. Interesting. Okay. I think this might do it. Okay, I'm looking at, okay, real quick, I'm just like perusing over this other code on the render pass color attachment. One thing that they have that we don't is they have a clear value. And that's just like what the clear, like when they clear the screen, what color is it going to be? So it looks like we're looking at a gray color. So I'm doing that. Let's keep looking through here. Okay, so we did the same stuff. Okay, we did the same stuff. Oh, complete guess. It looks like this is wrapped in a render function. I imagine that's so that we can call it multiple times. All right. So let's see if we get the red triangle here. I'm pretty sure we won't. And then we can figure out why. Okay, let's unbreakpoint this. No. Stop. Restore. Okay, well, we got a gray screen. And we didn't get our red triangle, but I think I know why. And this is why. We only have one vertice that we hard-coded. So we need 3 vertices, I think, to get our red triangle. So let's do that real quick. And let's just do it in on the fly here. And so this, before we do that, let me go back over here and let's talk about where you need to put your vertices. And they have a whole bunch right here. So we can maybe just steal these ones. But by default, the screen in like WebGL and I guess in WebGPU is in clip space. So, the left side of the screen is X -1, the bottom of the screen is Y -1, and vice versa for the other side of the screen. So if you're looking to like orient yourself on like the extents of the screen, that's in clip space. So you can change that with some clever tricks so that things are different if you want them to. It's generally a good idea to stay in clip space for the reason that floating point numbers. So let's say we change this to be like 1080 by 1920, or 1920 by 1080. That's all well and good, and you can totally do that, and it will work for you most of the time. The trick is you have more resolution in floating point numbers. Like, floating point numbers are a finite representation of like numbers, and you have more representation between 0 and 1 than you do between 0 and 1920. So, for example, so there's like bigger gaps in between the numbers. So I don't know if it's superstition or not, if it actually is a problem. But generally, that's why you stay in clip space, as far as I know. If someone knows better, you let me know, because that's the reason I've heard to stay in clip space. But it can be convenient if you don't care. Like me, sometimes you might just do some tricks to make this not be clip space. Okay, so let's grab this code here and paste it into our vertex shader for our vertices. Yoink. And I'm just gonna comment this out, and then we're gonna paste that in there. And let's understand this. This is a very different array initializer than I'm used to. So this part I'm following here. We're saying, okay, we're gonna declare a position variable, and then we have this array constructor, and we're saying, okay, we're gonna have an array of vectors with 2 floats, and we're gonna have 3 of them. And it looks like we can initialize each of these like so. So top center is 0. Remember, 0x is in the middle of the screen, and then 0.5 is 0.5 up the screen towards the top of the screen. Then we're going to the left in clip space. We're going -1 1/2 to the left and -1/2 down, and then we're going 1/2 to the right, and we're going -1/2 down. Okay, that makes sense. And we're in clip space again. So if we take a look at that, that tracks. So we'll have a triangle that looks kind of like, that's drawn like yoink, yoink, yoink. And we have that vertex index. Remember, looking back here, we have this magical built-in that we have that we can call any from the Aether. We can call into WebGPU and say, hey, give me the current index of the vertex you're drawing. And since we're only drawing 3, we'll only draw 3. And then we can return a vertex that we're interested in. So out of this little array. So I can paste that down. Slick. And then their vertices will all be red, the color red. So, you know, if we think about this again, like how vertex shaders work, it's like we're going to go through every vertex. We have 3, and we've hard-coded them in the shader, which is generally not what you do. You'd put this in a... I think our next refactoring after this is we'll move these into a buffer. So I think that'll be our next refactoring after we get this to work. But we're going to draw all 3 vertices. And, you know, return them out. And then once we have a vertex figured out, that vertex's color is decided by the fragment shader, which in this case is just always returns red. Okay, let's make sure that that works. Hey, look at that. That was a lot of effort. Let's see, how long have we been streaming? That was a lot of effort to get red triangle and explain it. Let's see. Sweet. Well, awesome. You're working on a CAD physics engine in Rust that is pretty slick. Yeah. I've been looking at Rust, and you let me know. Does this look like Rust to you? Does this look Rust inspired? The WGL syntax. I kind of in the back of my brain, it looks like maybe it's Rust. Yeah, that's super cool. Awesome. All right, cool. So we got our triangle. Let us see here. I think, yeah, I think our next refactoring is going to be, let's move this into a buffer instead of hard coding it in the shader. That seems like a bad move. So let's go back to the code and see how we make a buffer. Let's see. Does this thing have any helps for us? Nope, it doesn't. Cool. So this is we're off the rails now. Let's go take a look at MDN real quick, the source of all knowledge, and look at MDN WebGPU. How does one create a vertex buffer? Oh, I think I wanted this one. Cool. So this is the set part on the command encoder, but that's okay. We can start there. Or not. It doesn't really help us. Let's see. I want to create a buffer. How do I create a buffer? I saw create buffer in here. Create buffer. Okay. Create buffer. We got a couple examples here. This looks like what I want. Vertex. It's even named vertex buffer. Perfect. All right. So let's take a look. Oop. I did a thing I did not mean to do on my other screen. Well, whatever. All right, so let's go ahead and create that vertex buffer. Let's see if we can understand this. so we need to make it a certain size. It looks like we have a float 32 array, so we need to use a type array for the positions. We're doing 2D triangles here, so I don't think we need to specify the Z and W coordinates to keep it easy. All right, so let's refactor our triangle here. All right, so I'll just call this geometry. So let's create our vertices for our triangle here, and we have to use a typed array. And the only real difference between these and one of these in JavaScript is one of these can hold any kind of thing. This typed array is what it sounds like. It can only hold float 32s in it. And this is super useful for folks that are doing like this kind of programming where you need to communicate with hardware and you need to like guarantee that the array is contiguous versus like one of these, like, you know, you have no idea where the objects for this thing are living in memory. A float 32 array is guaranteed to be contiguous in memory, or at least it's going to look contiguous to things in memory, you know. So this is like for that low level stuff that you need. Also, if you're like really like trying to squeeze performance, you might start like looking at typed arrays as a way of like squeezing performance. But that's all that these are. Okay, so let's look at our hard-coded data here. So we have our vertices. We have 0. So I'm just gonna enter these as like x, y. So we've got 0, 0.5. We've got negative 0.5. And remember, these are all in clip space, where negative 1, 1 is the bottom left of the screen, and positive 1, 1 is the top right. And then our last vertice. You know, we're doing the leading 0. We don't need to, but we're doing it anyway. Cool. So we got our vertices in a float 32 array. Then we need to create a vertex buffer. And a buffer is just a fancy word for a array. Really. It's a place to store data. It looks like we can create any kind of buffer, which this is kind of nice. In WebGL, you needed to call, there's different buffer commands that hang off the WebGL global, and then you just have one here, which is actually kind of nice. So let's see what we have available to us here. So we need to say how big it is. So size 64, so I'm assuming that's a 64-bit int is the size that we can put in. I don't know. That's what we should probably look that up. That seems like I mean, we're not going to hit that limit because we got we have 3 vertices, and so we need to store 6 numbers. So I think we'll be okay. Usage flags is the other thing that is required. So let's take a look at that. That's a number. Okay, well, that's not super useful. What are our flags? Do we have any usage flags? GPU buffer. Okay, hold on. There's a couple links here. There's map read and map write. Okay. Or no, that's mapped at creation. What are the usage flags? Okay, let's look for usage. Doesn't say. Well, we're gonna go ask MDN. I think MDN will tell us what we need to know. Let's switch over there and let's ask MDN what the buffer usage flags are. Oh, it's right there. Okay, we got vertex and copy dist. Well, those are all well and good, but what do they mean? What does that mean? Let's see. Map read, copy dist, storage, copy source. Okay, well, it would be awesome if they told me what they meant. I've got a lot of examples, but not a lot of what do they mean. That would be super helpful. You know, I might have to look at the spec. Oh, here we go. There's a table. Ah, found it. Okay. What do these mean? Okay, so we have copy source. The buffer can be used as a source of a copy operation. That sounds all right. Buffer can be used as the destination of a write operation. Okay, so like you're trying to write something to it. So we probably want copy source, right? Because we have a bunch of vertices that we want to copy to the GPU. So that's probably a thing we're going to do. Index buffer. So I talked about this a little earlier in the stream, but index buffers are used when you don't want to repeat yourself. So say you have, you're going to reuse geometry in your vertex buffer. An index buffer might be what you use to point at like reuse indices. So like say you had a triangle strip. Instead of like having to specify multiple indices multiple times in your vertex buffer, you can use an index buffer to save space. It's generally a good idea to use index buffers if you can. Okay, that was an aside. Okay, indirect command arguments. I have no idea what those are. I don't think that's going to be a problem for us, but indirect commands. I have no idea what those are. Can be mapped for reading. This flag may only be combined with copy dest. I wonder if this is more for compute shaders, like you want to read the result of a buffer. Map read. Map write can be mapped for writing. Can only be used with copy source. Query resolve. Query results. I imagine that's for compute. No idea. Storage. Storage buffer, for example, a resource in a bind group. You know what? I'm not sure what you'd use this one for either. Uniform buffer. Yeah, I know what these are. This is if you have something that is going to be the same for every vertex and pixel on your screen during a render pass. So you might have a list of uniforms that you want to store. It looks like the only way to do it in WebGPU is uniform buffer. So that actually is super nice. And then vertex buffer. Okay, so I imagine we want vertex and copy source, right? And that's what we were looking at here. I've lost my tab. That's what we were looking at in one of these examples in MDN. We're gonna have to close some tabs here, I think. Here we are. Okay, so we're back to where we were. All right, and that's okay. And now we have arrived at our original. Okay, but this is unexpected. This is copy destination. I didn't expect that. I expected copy source. Contain all the vertex and copy dest. You indicate the buffer will be a vertex buffer, and the destination of copy operations. Well, I don't want it to be a destination. I want it to be a source. Interesting. So I'm going to do source, and then I might be wrong. So let's go back to our main. And we'll create our vertex buffer here. So we're going to have size. So we have 6 vertices. What, 6? What is it? 6, what is this, byte? Okay, this is byte length. Okay. I can actually grab this right, oh, it looks like I can just grab this right off of the typed array. That's nice. So that's would be like, what, float 32 array. So each of these is 32-bit float. So it's 32 times 6. I'm curious if I'm right. We'll just log it, and we'll look at that in a second. I'm curious if that's exactly what it is. I'm sure it is, but I could be wrong. Okay, so, and here's our usage. We know it's going to be a vertex, and then we're doing bitwise ORs here. We're setting the multiple flags at once. This is classic old school flag setting. I don't know if any of you've seen this kind of stuff before, but this is an old school way to do it. So, all right, so we're gonna do vertex, and then I said that I wanted copy source, even though that example I'm looking at was copy dist. Let me just reread copy source to make sure that I think that's what I want. This buffer can be used as the source of a copy operation. Okay, and then copy dist. This buffer can be used as the destination of a copy write operation. For example, copy texture to buffer. I think you want copy source, right? Well, I could be wrong. We'll find out. All right, so we need to get this vertex buffer. We have all our geometry. We need to get this vertex buffer into our shader as an attribute. So the first things first, we need to set a vertex buffer. So, okay, so we got a vertex buffer. Set vertex buffer. Slot. Okay, let's see. What is a slot? I'm assuming slot is just a number. And we got a buffer and we got an offset. Well, I'm gonna assume it's 0, but we're gonna go look that up. Vertex buffer, and then offset in bytes. We don't have to skip in, and then size. We don't have to do that either. Size in vertex. Minus offset. Okay, so we don't need to do that unless we're doing something funky. So that should be all we need. Out of curiosity, I wonder what the output of this is so far. Okay, so it still works. Awesome. Okay, so we've got our vertex buffer. How does the shader know about the vertex buffer? That is the next question. We need to have some way of telling each part of the vertex buffer, or piecing each part of the vertex buffer apart in the shader. And how does this work? There's got to be a way. Here. Okay, so here's what I'm going to do. We're going to go and Google MDN WebGPU vertex shader. So there should be some examples here of how to get the vertex buffer into the shader. Okay, so we already are seeing this location business in the shader. So that is telling us that we can input the location and color of a vertex. Right now we just have a location, and we don't need to do anything with color yet. So let's make that refactoring here real quick in our shader. So let me switch back to the shader. So instead of this built-in, we're going to say, okay, location 0 is going to be our position. And that's just going to be a vec. If this is anything like WebGL, you can tell it to be a wider type than you have, since we only have 2 of the vec4, and it'll just make the rest. Well, maybe not. Hold on. I don't want to assume. Let's just do the 2, and then if that doesn't work, we'll find out. Okay, so then I should be able to return a vec4 out of this. Okay, so you can, as the first argument of a vec4, you can give it a vec2, and then we make the z and the w component 0 and 1, since we don't care about them. So our vertices should then come in through here, assuming I set up the stuff right, the attributes right. And let's see, is that all I need to do? Let me hit save. Let's see if it works. It definitely does not work. All right, let's take a look at the error message that we got. Okay. Oh, let's see if I was right on that calculation. Float 32 times 6. And I am not right. Okay, well. Vertex attribute slot 0 used in shader code entry point was not present in vertex state while calling create render pipeline. Okay. I love these error messages. So pipeline is invalid. And then we got some C++ errors. Okay. I think I know where to start. So the first error here is saying our vertex state is wrong. So something is wrong with our vertex. And maybe it's in this render pipeline. So let's see what we can do here. So we got vertex. Well, let's start with vertex. Oh, there's buffers. Okay, so I betcha we gotta put a buffer in here. Our array stride in bytes between elements of this array. I think we have a stride of 2. Step mode per vertex. And then we have this. What is this? We have format. Okay, this is looking like this is what we need. We don't have the offset that we care about. Numeric location associated with this attribute, which is going to be 0. Location 0. Ha! Okay, so this is exactly where we need to be. Okay, so let's go do that in the buffers in vertex. So we need buffers. What was this? Array. And then we have one buffer. Attributes. This is location 0. And let's see. Let's go look at MDN here real quick and look at the render pipeline and see what it's supposed to look like. MDN create render pipeline. Okay, so we got vertex. Module, buffers, okay. I think I got the types wrong here. Okay, so that is an array. So we need array stride. Stride in bytes between different structures, i.e. vertices. So we need to stride, what is it? We've got a vec2, vec2f. Vec2f, that's two floats. Floats are 32 a piece. Oh, I forget which one this is going to need to be. Because it's either, okay, so it's the number in bytes of different data structures. So we got 4 bytes. Okay, so we got 4 bytes per float. And we have 2 floats. Don't know if that's right. I'm going to write down my assumption here. All right, and we have 2 floats in a vec2f. Right? That seems right. I might be wrong. Okay, so I didn't have my screen shared. Okay, I have the types wrong here, but I'm working through the parameters that we need. So we have attributes. So attributes needs a format. And that is a float. I think it's float 32. I think that's what we need. And I think these, if this is anything like WebGL, the X means it's like a matrix type, but I could be wrong. Let's go and look at the definition in MDN real quick as it loads. Okay, so we have a table here that helps us out. Okay, so we have a vec2 here. So in our shader we have a vec2f. So I can use. Oh, maybe I do need to do this 32 by 2. Okay, I think I'm glad I looked at this. Okay, so we have vec2f, so that's a float 32 by 2. I'm gonna link this in the code. Okay. And I broke the build. Okay, so there's that, and then we needed one more. We have format, offset, shader, location. So we need offset, which is 0. Cool. Okay, so we've got, theoretically, we've got our buffer, like metadata set up. So we're saying we're going to have a buffer. It's going to have a stride of 2 bytes per float, or 4 bytes per float, per 2 floats for a vec2f, I think. Because 32-bit integer or 32-bit float is 4 bytes, so that math checks out in my head. Maybe I'm wrong, but we'll find out. We're not doing anything fancy in the buffer, so it's 0, and then we're going to put it in shader location 0. 0 connects with slot 0 here. And then we have, okay, that's where we wire it together. And then our shader is location 0. So it all checks out, theoretically. Let me delete this. It all checks out. Okay, so let's go check our code and see how we're doing. We are not drawing a triangle. And now we have no errors. Woof. This is like the worst possible situation to be in. No errors and nothing drawing. All right, well, let's think about this. We've got our vertex buffer, theoretically. We've got it set up, theoretically. We have the right stride. We have... Okay, let me get back to the code here. It's not complaining. We have our position. We have the same data that we had before. The only thing I can think of is our stride is wrong. Let's look at MDN again. All right, so this looks very similar to what we've got. They're doing an array buffer, and they've got vertices. They got 4 vertices per. This looks pretty similar to what we've got. Okay. This looks pretty much spot on with what we've got. So it must be something silly that we're missing. So let's take a look here. The only thing I can think of is I was wrong on this flag, and it isn't copy source, but it's copy dist. Let's try that, and then try to understand. Okay, it's not that. Back to MDN. One of these tabs. Okay, so it's not copy dist. Let's go back to copy source. I think if we can get this triangle rendering with the vertex buffer, I'll be very happy. Oh, hello. We're writing a buffer here. That is not something we're doing. So we're creating the buffer here. You know what? But do we ever actually put these vertices? Oh no, we never actually put these vertices in the buffer. Oh my goodness, that's what it is. So, all right. So I think I figured it out. We created a vertex buffer just fine. But there's nothing in it. So we created the vertex buffer here, and it wires up just fine, but it's an empty vertex buffer, which is why we're not seeing anything. So we have to actually write the data into the vertex buffer. Which makes way too much sense. For some reason, I guess I thought that it was just magically figuring it out. If someone saw that and was like pulling your hair out, I'm really sorry. But yeah, so that's the reason I don't think it was working. So, and then we do need to make this copy dist, right? Because we need to write into the buffer. That makes a lot of sense. That's why they had copy dist. Let's see. Do we have a triangle? Oh my God, we do. I'll show you the full glory of a red triangle that took us 2 hours to draw. So, okay, that wasn't too bad though. I think all in all that we now have a vertex buffer piping our data through. We're able to draw stuff. Let's go for bonus points. Let's try to draw a texture onto WebGPU. And then I think if we can do that, I'm gonna call it. But this is pretty cool. All right, so I think I'm grokking this now. We've got stuff being drawn. and it's coming from a vertex buffer that we actually wrote to. So I'm going to go ahead in the comments here and say that we actually need to fill the vertex buffer and so okay, neat. Let's see if we can figure out if we can bootstrap ourselves here on the loading a picture, because a red triangle is great, but if we're going to make the next Vampire Survivors, we're going to need some sick sprite artwork. Otherwise, this just won't do. So let's go to WebGL fundamental or WebGPU fundamentals, and let's see. I think we let me just like really briefly go over the diagram here that we've completed. Took us a while to get there, but I think I'm understanding how WebGPU is working. So now the thing that we just did was we figured out the vertex buffer bit of the pipeline. So we've created a vertex shader, fragment shader. We have a vertex buffer now that is feeding our vertices in. And then we have a render path set up, and the color attachment is set up to our canvas. So bam, we got that working. Now we need to figure out how this texture business works. And it looks like that's going to go through something called a bind group. And then we'll be able to pass that through, theoretically, a vertex shader or fragment shader, or fragment shader to influence the color that gets outputted to the canvas. Cool. So let's figure out if WebGL fundamentals, or WebGPU fundamentals, has a texture. Let's start with textures. Cool. All right. So textures are just, what do you think of them? They're just pictures. And then we just need to take that picture and draw it. Let's see. Okay, they've got a quad here. Okay, so let's draw a quad. That might be a first thing to do, because we're going to have to put the texture on something. So let's draw a quad. So let's go from 0 to, I'm just going to steal their code. We're going to go 0 to 1 to 0. So 1 is on the right. So 0, 0 is the center of the screen. So we're in clip space, remember. We're going to go 1 to the right, and then 0 is kind of in the middle of the screen. And then we're going to go up to the center top. Okay, so that's the first triangle. So then we're going to draw triangle 2. We're going to go from that same vertice at the center top. We're going to go to the right and down, same vertice. And then this is the new vertice, which is 1, 1. So we're just in the top right corner of clip space, which is fine. Cool. How do we load a texture? Let's take a look at that. There were two uniform storage data textures. Textures represent a 2D image. 2D image is just a 2D array of color values. What makes texture special is they can be accessed by a hardware sampler, which can be used for blending or scaling. Okay, we see this example of a sampler running, I guess. Cool. Texture coordinates are sampled in textures from 0 to 1. across and down. So if you've ever if you're familiar with like UV coordinates, this is kind of U and V. So we're looking at that. There's a previous article, but I don't want to use it. Okay, so it looks like we have a texture coordinate output that they're using, and that's the vec2f. Cool. And we're using that in our output here. Okay, so we decide what texture coordinate we're using based on what? Based on the position. So we're just using the same. Oh, so they're using, oh, that's why they did 0 and 1, is they're using the same. Okay, so that's why they did that, is they're using the same coordinate space as UV so that they don't have to worry about mapping the texture coordinate. Okay. That's fine. We don't need to worry about that. I think we'll be fine. We have some new attributes that I haven't seen before. There's a group and a binding. Binding group. So group 0 binding 0, group 0 binding 1. Okay. That seems to track. There's a sampler and a texture. All right. There's texture data. What is this? Oh, wow. We're just creating handmade texture data in this one. Well, I don't want to do that. I want to load an image. Let's do that instead. Oh, that's wild. Okay, so let's see if we can load an image instead. Let's go to NVM instead. WebGPU texture. All right. Let's go find textures. Create resources containing your data. I would like to load a texture. I would like to load a texture. This is our color attachment, so we already know about that one. A GPU external texture. GPU texture. A texture, a container used to store 1D, 2D, 3D stores rate of GPU. Okay, so I think we want this. How does one use a texture? All right, here's what I'm interested in. All right, that's cool. Let's get an image here. Let me grab an image off of Excalibur. So I want to grab the sword. Let's get the pixel sword and then let's render that. Actually, let's just go to GitHub. Assets. Let's grab the sword. Let's grab the smaller sword. There we go. Don't look at my downloads. Okay, so I'm going to download this. We're going to throw it in the WebGPU. We're just going to throw it right at the top of the WebGPU project here. And then we're going to go and take a look at how to do this. All right, so we need an image element. I don't need this meta URL. I just need the image. We need to decode it. Create image bitmap. What is this doing? Create image bitmap. I don't know what that function is. So we create a texture, and then we copy it in. Okay, like we did with the vertex buffer, we had to write into the texture handle. Okay, that doesn't seem too bad. I don't know what this function is though. I don't know where this create image bitmap. Oh, that's just built in. I had no idea that was built in. Cool. So let's do it. That seems like really doable. So this is there's the icon I downloaded. So we should be able to load that if Parcel will let me. So I think what I need to do is I need to do some magic here to make Parcel happy and TypeScript happy. This is just so I can, I'm doing this so I can import it at the top here. Import. That way I can import it like this. And this will allow me to have the file path of it after Parcel builds it. So that's the only reason, because if I didn't do this files thing, this .png would throw an error in the import. So that's the only reason I did that. So let's go ahead and load our image. We'll just do it right before we do our vertex data stuff. So create a in-memory image, create element image source equals image sword png. So that should be the source theoretically. Oh, hold on. I need to make this a I think that's right. Nope, that's not right. Hold on. I know the answer to this. Let me find the example to make TypeScript happy. Oh, here we go. This is the incantation that makes TypeScript happy for this. There we go. So we're saying that this is a string value that comes through, because that's what it is. And now TypeScript is happy. Cool. All right, so then we need to wait for the image to decode. This, if you didn't want to do this, you can do on mode, which is the same thing, but callbackified. So decode just allows you to do it in async await. Bitmap is that function I didn't know was a thing. Create image bitmap. Wow, had no idea that was a thing. That's just in libdom. That's just part of the browser, and I had no idea. That is so wild. And you can just pass that in image. What does this return? Image bitmap. Is this just the thing that goes into a canvas? Nifty. All right, that's just a bitmap that you can use. Okay, so then we have that sword texture that we need to create in the GPU. So that's create texture, and there's a lot of parameters here. So let's go take a look at what we have. What do we need to do here? So we need size. So width, height, and depth. So, or layer count. So this is not a 3D texture. So width and height is going to be whatever the width and height of the image is, and then 1. We don't care about maps because we're not doing any weird sampling right now. We don't care about sample count because we don't care. Dimension is optional. Whether the texture is one-dimensional, two-dimensional, or three-dimensional. Interesting. Well, that's optional. Let's see if we can get away with not doing that. I want to say it's 2D by default, but yeah. Format. I don't know what that's going to be. I'm assuming that's going to be whatever the platform is, but we have to say the format of the texture. How do I know that? Yeah, we're going to have to pick something there. I'm not sure what that's supposed to be. Usage. Okay, we got more flags. Let's see what usages we can have. All right, so it doesn't really tell us, but if I look at the browser, there's texture binding, copy destination, render attachment. I think so. Texture binding makes sense because we're going to need to use it as a texture. Copy destination makes sense because we're going to have to copy our bitmap into it. Render attachment, I don't know if that makes sense or not. And does it have? Nope, doesn't help me out. All right, so let's go figure out what render attachment is. Maybe we need to go to the spec. Nope. Wow, really nothing in the spec? Oh, that's Wigzel. Oh, I'm looking at Wigzel. Never mind. All right. Must have render attachment. Let's look at the spec. When in doubt, look at the spec. Okay. The texture can be used as a color or depth stencil attachment in a render pass. Okay, so it looks like this is, okay, these are the possibilities. GPU texture usage flags. Okay, so copy source is the source of a copy operation. Dest can be the destination. We want that texture can be bound. Uses sampled texture. We do want that. Render attachment. I don't know if we want render attachment. Color pass attachment view. I don't know if we need that. I lost my place. Okay. I don't know if we need that. I'm going to omit it for now, and then we'll find out if we need it when it doesn't work, like I did last time. Okay, so let's do usage first, since we were just talking about that. And we'll do GPU usage. Copy is what we need, and we need texture binding. Then we need GPU texture usage. Oh, I said I wasn't going to use it. So let's just not use the render attachment. Format. I have no idea what the format here is going to be. Look at all these formats. RGBA, unorm, uint. I have no idea what this is going to be. I mean, I think what I'm going to do is I'm just going to grab the presentation format and see if that works. And size is the easy question. We got an image. We got a bitmap here with a width, height, and one deep. And then I missed a comma here. Okay, so we got a texture handle, and then we need to write into it with our actual image bitmap that the thing that I forgot to do last time. So we need to copy external image to texture, So we have a source here, image bitmap, which is bitmap. And then we have our texture handle, which is word texture. And then we need to specify the width and height again. I'm just going to grab this. I'm going to look at the types here because I want to know what's possible. We got source and destination. And then copy size. And that's, I'm assuming, the width and height here. Yeah, okay. So source, what can source be? So, okay, cool. So we can use image bitmap. We can use other canvases. We can use an off-screen canvas. That's kind of neat. Oh, we can say what the origin of the copy that we're copying from. Oh, and sometimes you might need to flip the Y depending on the texture. So you might need to, if it's upside down. You needed to do that in WebGL a lot. And then pre-multiplied alpha, normally yes. Does it do it by default? Normally the answer is yes if you want to be more efficient. You want to pre-multiply your alphas. Usually the answer is yes. But we won't do that right now. We'll just do the default, the basic stuff here. Okay, so theoretically we've got everything passed in. Now we need to wire it up. I imagine we need to add it to the render pass. Set texture, binding. Okay, bind group. Okay, so this is something I don't know about. So bind groups. Let's figure out how to get textures in here. So let's take a look at the example here. We just have the texture here, but we don't really get a lot of information about what's next. Let's see. So let's look into the bind group and see if there is any examples. MDN WebGPU texture bind group. Okay, so this looks like it's for compute. Visibility, compute, not helping me. Maybe this WebGPU fundamentals will have something I can use, because I'm not using the raw texture data, but I am interested in a bind group. Here we go. Here's a bind group. All right, so we did, okay, so they wrote their own texture stuff, but we're gonna need to do our own sampler. Okay. All right, so what we'll do is create a bind group here at 0. And then the bind group is going to have a sampler and our texture. Okay. Oh, and we just create a view. Oh, well, that's not too bad. And what do they use okay, let's just do that, because I think that makes sense. They have a sampler. I don't know if we need a sampler, though. But let's just do it anyway. Let me switch back to the code window here. So we'll create a sampler. And a sampler is just a way of sampling a texture and producing given like a raw bitmap, sampling that texture along like 0 to 1, like on the UV range, and giving you a pixel. Okay, so it looks like we can specify like, okay, this, we might need to mess with this options, because this is where we want, if we're going to do pixel art, this is where we're going to want to do nearest, so that when we when we're scaling up magnification filter, we want to do nearest to do that sharp jaggies, or linear. Let's see, and then we want to clamp to edge if we want to do the, okay. So I'm gonna take a guess at the sampler parameters that we want. What do we want? Mag filter, we want nearest. Min filter, we want nearest. For those sharp, jaggy edges. We don't want a tile. Was it U? We want clamped edge. And V, we want clamped edge. So no tiling. We want it to just end. Cool. So that's not too bad. Yeah, okay. That's pretty good. Okay, yeah. So that's a sampler. And then we need to create a binding group to pass our texture, both our texture and our sampler, into the bind group, and then that'll be available in our shader. Nice. Okay. So far, I'm loving WebGPU more than WebGL. This is way better. Okay. I don't know what this means. Get bind group pipeline layout. Is this just like we grab, we just pick a number? Good question. So let's go read about that. What is a group pipeline layout? Method returns pipelines layout object at a given index. If the pipeline was created with auto, this method is the only way to retrieve group layouts generated by the pipeline. In our case, it is auto, so I guess that's what we got to do. Okay. So then we need to find the tab that I lost. And we have two entries in here. So we have the sampler and we have our texture. So we're gonna pass the sampler in, and then we're gonna get the texture in, which is sword texture. And then we gotta create a view and have a comma, and then we need to set our bind group, which is 0, and then we have our bind group. Cool. So that should pass it through to our shader. And I can already tell that I needed to add that render attachment thing that I was talking about earlier, because it's blowing up on my other screen. So destination texture needs copy dist and render attachment usage. So we'll add, that answers that question. We need a render attachment. I am so far loving the error messages, because this is like way better than WebGL, where you'd be like, it just didn't work, and you'd be like, and it wouldn't give you any error. It'd be like, what? You'd be like, oh, I'm in the wrong thing. You'd be like looking at a screen that's not working with no hint. Okay. Cool. So that error's gone away, but we got a new one, which is bind group layout index 0 doesn't correspond to a bind group for this pipeline. On render pipeline. rsig triangle render pipeline. Let's go look for that. rsig. Oh, okay. So we must have to add a group layout in here as well. So we have buffers. We probably have bind group. All right, let's go look at the types. Let me actually go back here because you missed that. So that error message that we had right here, render pipeline is the object that's broken. I went and searched for that, and that's the label that we had right here. Freaking magical. It's wonderful. It's just a wonderful thing. It's beautiful. I've never had an error message that useful in my entire life. That's so great. This is where it's broken. Okay, so let's go look. We must need to define our bind group in the pipeline, which makes sense because if we go back to that, if we were to go back to that diagram in the that I was showing earlier, I think we had to have the pipeline defined in here. Okay, so it's not in here. Is it in the vertex? It's not in here. Is it in buffers? It wouldn't be in a buffer. Doesn't make sense. Is it need to be in the fragment? Which is where it probably makes sense. No. Okay, where does this need to be? Bind group. Where do the bind groups need to be in your pipeline? Let's see. I'm going to look at this example here. Bind layout. There's nothing that really is standing out to me. Interesting. That is most disturbing. Well, it's complaining about our render pipeline. It's got to be something about this that it doesn't like. Is it something to do with our shader? Does it need to have... Does the shader need to have like definitions in the shader code for those bind groups? Maybe? Let's try that. Let me throw these in here and see if that... Let's see, what did we call these? We called it texture... Binding 0 is that and sort texture. Okay. So it doesn't matter the name, but it's we just have the binding. So 0 binding is sampler, and I'm just going to call this sampler. Or do I need to name it something different than a type? Okay, I'm just going to call it this. Okay, let's see what happens in the code. Still doesn't like it. So it wasn't that. I'm going to comment that out for now. Oh wait, I got a different error. Bind group layout index 0 doesn't correspond to... Okay, so if I comment this out, I get the group layout index doesn't correspond. If I add this back, group layout doesn't correspond. Okay, so no, it's the same error. I thought it was a different error. Invalid bind group. Set bind group. Bind group is invalid. So it doesn't like my bind group. I'm not sure what's wrong with it. I created a bind group. we got the layout from the pipeline, which we have defined. Where did we define our pipeline? That's our pipeline. And we didn't need anything else in here in our pipeline. There's no primitive. No. Vertex. No. Multi-sample. No. Yeah, so it doesn't look like there's anything we need to define in here, except for maybe the layout. Maybe layout is wrong. Having layout auto is a mistake. Looks like that's kind of the only way of the game here. It looks like it's only auto. So I think this is still right. Well, if anyone in the chat has an idea, let me know. We're making such good progress. Well, bind group. While validating get bind group layout doesn't correspond to a bind group in this location. That is throwing me. Created the texture. Created the sampler, created the bind group. We have the right bindings. We got the pipeline layout. We've got the pipeline set. We've got our bind group. Do I need to do this like before I set the pipeline? Is it like a weird order of operations thing? No, it doesn't seem to be that. Setting a vertex buffer is fine. Setting a bind group. We're only drawing 3 of the 6 vertices. We actually probably should draw all 6. Yeah, it's kind of blowing me away. I'm tempted to think that there's something wrong in our shader. Let's try sampling the texture. So So we'll just add, we'll go at the 0, 0 coordinate and see if that'll, oh, that worked. Holy crap. Okay, so it looks like we needed to actually use it. What the heck? Is that really it? It's like if you have an unused thing, it's an error. Oh, it's totally that. So that threw me. Okay, so if you have unused bindings, it throws an error. That is super, super obtuse. Okay, so that's the deal. All right, so let me show you the code that is running now. So we're sampling at 0, 0, which is returning black. Let's see if that makes sense to us. That is not making sense, but that might be because of alpha stuff. So I'll reserve judgment. Perhaps the alpha is not working properly. Because 0, 0 would be up here, and black I think would be. Let's see if I can like sample in the middle. Maybe that is giving us a different color. Yeah. So if I sample in the middle, I get like what looks like the middle middle pixel here of the sword. So it looks like it's working. Huzzah! So now all we need to do is get that texture coordinates into the vertices. So we just need to tell it what texture coordinates it needs to load at each vertex, and then we should see a sword rendered in the picture. So this is going to look very similar to, like, as far as I know, to the position. In fact, I bet we could like add another buffer here and do like, you know, have UV come through here, and then that would be our like our UV coordinate. So let's try that. We'll need to output, in addition to outputting position, we'll need to save that UV, because we don't need the UV in the vertex. We need it in the fragment. So we need a struct to hold our position, our output position. So let me we'll call it vertex output struct. So we'll hold our position, and then we need to hold on to our UV coordinate, which is also a vec2. Sweet. And I think if I'm looking at this right, oh, hold on. I don't want to do position there. I want built-in position, because we're going to output to the built-in position. And then I want to output to location 0, which is just a slot that we're going to store that information. So I want built-in position to be in our output. And then I want to stash the UV so that we can suck that into the vertex shader later. So, okay, so in here we'll need to do, I think this is fine to do this the way it is. I need, this needs to be, what did I change here? Let's go back. I'm confusing myself. Okay, so, okay, that's fine. All right. I thought I had changed that from built-in to location, but I hadn't. Okay, we're outputting. This is going to be the new output. So this is going to be the new output here. Vertex output. So vertex output. This is just a struct, so we'll just declare it here. That should we'll grab the position that we were just returning before. Now we're just going to set it to the output struct. That should return it the same way. And then we need to also set our UV, which is just UV on the way in. So that should work just fine. And then our vertex, we're going to sample based on our output here. So instead of sampling the middle, we just need UV. Okay, that should work. As long as we wire up our UV stuff to be passed in, that should work. I'm gonna save that and it's gonna break over here. Oh, I need to add some semicolons. No, is that not it? What am I missing here? Oh, they need commas. All right, let me show you the errors that I'm getting. Store type of built-in position must be vec4. That is true. That should be a vec4. Position needs to be a vec4. All right. Slot 1 is not present. That's true because we haven't done it yet. So slot 1 is this guy. So UV. So we haven't put our UV coordinates in there yet. So huzzah. That error made sense to me. All right. Let's go and do UV. So we have our geometry here. Let's do our UV at the same time. So we'll need a UV coordinate for every vertice that we have. So we'll need another 6 vertices. So actually, we probably can just steal all of these since they're on the 0 to 1 space. But then we can adjust these later so that they're not the same. So, but I think this actually just works just by accident because they're on the 0 to 1 space. So let's create a new handle for our UV. And then we have our UV size, byte length. And then same deal here. And same deal here. So we'll write into the UV buffer our UVs. And we're going to write them all. And then we need to update our slot in the buffers here. It's mostly the same. And this is location 1. Okay, so still did not work. But vertex buffer slot required by pipeline was not set. Oh, you know why? It's because we didn't set it in here. Huzzah! Check that out. It worked. I gotta switch the screen here, but it worked. UVs. Baby! We've got textures. Nice. Pretty slick. All right, so let's clean this up a little bit, and then I think we're gonna call it. This was pretty productive. I got a texture in there, and we got it all working. I am going to go ahead and check this. I'll check this in and I'll push this repo up so that folks can go check it out. And then we'll wrap up the stream. But let's do a quick cleanup here of the code. And I really want to define this geometry differently. I kind of want to make a create quad function. Where you can create an x, y, width, height. Let's do a create quad, and we can start with this. So in clip space, okay, so we got 0, 0 is the center of clip space here. So center of clip space is like right here, right at the bottom left corner here of the sword. So what I really want to do is I want to create the quad from the top left. So I want to create so I want x plus really I want to go from the top left. So I'm going to go from the top left vertice. So x and y minus 1. So that's triangle number 1 here. That's the top left. And then we go down on the x. Let's see. Are these using a clockwise or counterclockwise winding? So 0, 0 to 1, 0 to 0, 1 is counterclockwise. So we're going to go x minus 1, y minus 0. And then we're going to do, so that's top left here. Then we're going to go middle, and then we need to be our left middle, and then we just need middle middle. So that's minus 0, y minus 0. Cool, so that's triangle number 1. And then we need to share 2 of the vertices, which are x minus 0, y minus 0, x minus 1, y minus 0. And then the last vertice we need is the top right, which is x plus 1, y minus 1. Okay, so advantage here is now we can multiply the x's by width. Y's by height. And then we should be able to make a quad of any size, theoretically, if I did the math right. Which is very possible I did it wrong. So we'll save this for now. All right, so we'll save that for now, and then we're going to try to create a quad here. Let's new quad, or create, what is it, create quad. And I want to create one at 0, 0 that is 1 or 2 high and 2 wide. which would give us the whole screen. And then I want to do the same thing for... Actually, I want to keep the UV alone. Well, I screwed it up, so let's take a look. I definitely messed up my vertices, so let's take a look. We'll keep the old drawing method here, and what I'll do is I'll just I'll check this into Git, and we will call it a night, and I'll publish the repo. So let's do that real quick. Make sure there's nothing in here that we don't want to check in. I think we have everything working okay. Let's add a README. WebGPU live learning. Our requirements here are Node, JS, npm, run locally. We are going to run npm install and then npm start. I believe that's what we had. Sweet. That's it. It's a live learning session of WebGPU on Twitch. If I can spell Twitch. Let's grab the rest of the info here, and let's commit this. Oh, I need to log back in tonight. Oh, wrong browser. Need to log back into GitHub, and we will post this up, and then we'll call it a day. All right. Let's add all of these here. Cool. So we committed that, and let's add the origin and push it. Neat. Well, friends. Oh, hey, Comronicus. Yeah, pretty good so far. It's definitely way better. WebGPU is way better, like from an error perspective and development perspective than I think WebGL is. Like WebGL, you're just kind of left in the dark and grasping at straws. So I was able to like figure out the errors pretty easily just by reading the error messages, which is a novel concept. But yeah, no, it was pretty cool. I'm pretty pleased with that. So I posted that up, and we might revisit this here tomorrow, and we'll try to get some more fun things going. I have some ideas like doing like batch rendering, doing animation, getting all of those things wired in here so you can make a game here with like WebGPU. But this is a good start, and I think we got a good grasp and understanding of WebGPU here. For that, really, my first time touching any of this code. So I did have a little understanding of WebGL before I came into this, but this really wasn't too bad in terms of like interacting with WebGPU. It wasn't the worst. I was pleasantly surprised. So I'm going to probably call it there. If you would like, folks on the call, if you'd like to check out any of my stuff on GitHub, I'm at github.com/eonerheim. If you'd like to check out any of the other videos that I've done, my videos are going to be up on Twitch. I save the VODs. I probably will also post this to YouTube. So if you're interested in that, you can go check out my YouTube. You can also sponsor me on GitHub so I can do more stuff like this, or on Patreon. But yeah, if you enjoyed the WebGPU stuff, we spent most of the day doing, the basics of WebGPU programming and figuring it out together because I have never done it before. I have the example here posted up on GitHub, so feel free to grab that and clone it. Yeah, I think that should be it. Thank y'all for coming and spending 3 hours with me going through WebGPU. All right, we'll see you next time. All right, so last time we got some stuff rendering on the screen, and I need to turn off the feedback here because I am hearing myself. Okay, cool. Last time we got a sword rendering on the screen. Now that wasn't exactly what we had rendering last time we left off. There's actually a few things that I did off camera, but I want to talk about them because they're kind of important. Last time I was struggling to write a create quad function, so I did that. That was just an error between the chair and the keyboard. And then the other thing that I wound up doing was adding this flip Y. And let me take this out real quick because this is the way it was when we left off last time. Let's go ahead and refresh this, and you'll notice that our image of our sword here, where we left off last time, was upside down, which is not what we had downloaded here in our project. So why is that? So I believe this is because of the way that the GPU is expecting texture data. So according to this article from someone on the internet, they expect pixel data in a bottom down order, but when we load things from image, we go top down. So this causes the image to actually just be flipped vertically on the Y. So in WebGL, we have unpack flip Y is what we wind up doing. But in WebGPU, we wind up doing flip Y here when we copy to our texture. So that's the only difference between last time Dragon Ball Z and now. But I did want to show that real quick, so that we can get started with a few things that I wanted to touch on today. So, we just talked about why we need to flip the Y. And maybe real quick, I'll just review kind of where we are with the code. um, in relation to a diagram that was super helpful from this website, WebGPU Fundamentals. But let's just review where we're kind of at, and then we can kick into something new perhaps. So let's take a look here. Last time we got our first pipeline working where we drew a triangle, and then we went ahead and refactored that triangle out into a vertex buffer. And then we went ahead and made that into a quad. And then we went ahead and uploaded a texture and made sure that that texture was being loaded in, and that texture was being sampled. And we flipped the Y, and now we're drawing that to the screen. Now there's a few things that I think would be interesting to tackle next. I think that would be figuring out how to do transparency in WebGPU. I think another thing that might be interesting would be looking at how uniforms work. And kind of a quick review from last time, uniforms are those constants that are the same for every invocation of your shader for a particular frame. So one thing we might use that for is a projection matrix. So if we wanted to do a certain type of projection, that might be interesting to do as well, so that we can start moving shapes around on the screen perhaps, and maybe animating them as a stretch goal. All right, so let's get into it. So transparency, what is involved in transparency? Well, let's find out. In WebGL, you have to set a blending function, and you have to do a bunch of configurations so that things are transparent. But how do we do that in WebGPU? So we might need to do something with the depth buffer. Yeah, we might need to set a blending function. Let's see if we can figure that out. Let's see. Let's go back up to the top here. Let's see if there's anything on transparency. I don't see anything. Again, this is me not knowing anything about it in WebGPU and just learning it. So we're learning it together. One thing that I will take a look at here is this should not be a black background, so we'll know if we're working if the background is showing through the clear color. So let me make this quad like a little smaller, and then it'll be clear what the background is. Let me do that real quick. So let me change the quad from the whole, all of clip space to maybe a quarter of clip space. All right, so then we'll go back to the browser here. So we're in a quarter of clip space. So our background is gray here, and this should be transparent if we take a look at our image. Those are transparent pixels here. So that's what we would like to see. So let's take a look. WebGPU transparency. Let's see what's next. Looking at the spec. Transparency. All right, so transparency. Replace the drawing buffer, draw image. Drawing buffer, maybe transparent. Alpha mode. Okay, what is alpha mode? Alpha mode. Defaulting to opaque. Color space, device format. This looks like the context of the canvas. So this doesn't look like necessarily what is going to configure transparency. Let's see. GPU canvas alpha mode. Okay, so this enum selects how the contents of the canvas will be interpreted when read. I believe we want pre-multiplied. So I think we do want that to be on. You generally want pre-multiplied unless you have a reason not to. So that's the canvas configuration. So let's go over there and make that canvas configuration change. And that would be over here, this context configuration. So alpha mode, we want pre-multiplied. And let's see what that does. All right, so interesting. So pre-multiplied, we're getting a different compositing here. So that's very interesting. Yeah, all right, so pre-multiplied is white. That might be expected, and I'm just surprised for no reason. So color space is by default sRGB. Okay. Let's see. How do we make transparent texture? Why don't I start there? Let's do transparent texture WebGPU. Well, let's start with Stack Overflow. Okay, so there's some alpha blending. This is a different language, but blend state, alpha blending. All right, so let's go look at blend state. According to the docs, let's look at what this is. WebGPU, this is for Rust, I believe. But it should be similar. Blend state. Where do we use blend state? Let's look at the spec. All right, GPU blend state. GPU color target state. All right, all right. Here we go. These look like what we need. Blend state. This is color target state. Let's scroll up to the top here. Yeah, how do I use this? What is... Where are these used? I would maybe expect it to be used... Oh, you know what? I didn't have the spec up. So looking at blend state here, I would maybe expect these to be used in the color attachment in the pipeline. Color target state. So let's go over to coding. Let's take a look here at what we've got. in our pipeline. So we got our vertex, our fragment, we've got our color attachments. Let's see what goes on in a color attachment that we can mess with. Depth, stencil attachment, render pass. This looks like all depth. I don't think this is where we need to be. Let's look at color attachment. Clear value. Well, maybe we should give it an explicit clear color. GPU color. Yeah, maybe we should give it an explicit clear color instead of like the default gray. So let's do that real quick. Oh, let's go over here. Oh, and we did, which is gray. Okay, so gray is the number we picked, or is the amount we picked. What happens if we do 0? Okay, well that works. Cool. All right, so that works as I expect. Okay, so still, how do we do transparency? Let's find all references. Find all references. We're going to work backwards. GPU color target state. Fragment state. Fragment. Okay, so it is in the pipeline. So it's in the fragment. Describes the fragment shader entry point. So, okay, so, all right, that actually makes sense because the fragment is where we color every pixel. So actually that does make a lot of sense. This is where the types in TypeScript really help because you can work backwards. Okay, so looking at the fragment state, we can configure our blend state. And then we have our format here. So we already got that figured out. We have our blend state. So we have blend component, source factor, reverse subtract. Okay. All right. I forget what the right ones are. These are for pre-multiplied, but we'll find out together. I have an example of this somewhere. So let's go back to, I'm going to actually just pin this. And then let's go back to the main here and look at our fragment. So we already have target. We already have format. We want blend. So we want blend. And then we have our blend state here, which can be color GPU blend component. Okay, so we'll figure that out in a second. Then we have alpha. This alpha blend operation. Add, subtract, reverse, min, max. Okay. So blend factor. Source factor, dest factor. So let me look at what is recommended here in WebGL. Because I've done this once before. So we want color, then we have alpha, We have operation. We want to add alpha, I think. And we want to source factor. I'm looking at some other code where I've done this before for pre-multiplied alpha. The source factor 1 and dest factor 1 minus source alpha. Excuse me, 1 minus source alpha. Okay, so that's the blend equation for alpha. Do I need color? I'm gonna omit color for a second here and we'll start with alpha. Oh, maybe I need both. So blend state has both. So you need to specify color and alpha. Well, I don't know which one is which. I'm gonna say they're the same. We'll go with that, and then we'll learn together what the right answer is. Source factor 1, this factor 1 minus source alpha. As far as I know, this is the right constant for pre-multiplied alpha. So let's see how that looks. There we go. Hey, it worked. And just to be extra sure that it worked, we're going to go and change the background here real quick and see, you know, if we make the background like more red, that it worked. Hey, hey, how about that? We figured out transparency. Okay, so let's understand what I just did. So let's look at let's go look that up. WebGL transparency blend function explanation pre-multiplied alpha. There's a really good article about this. It might be this one. There's a really good article about this that I read originally, and this might be it. Yeah, I think this is it. So this is a really great article. And I've read it before, and I've not retained any of the information. So I'm going to post this in the chat here real quick. And if anyone is interested, they can go ahead and read that. But let's understand it here. Many people learn to copy and paste this function to get transparent blending, which assumes straight alpha, so not pre-multiplied. So if you don't have pre-multiplied texture, that's what this blend function assumes. So you have source alpha 1 minus source alpha. And that is referencing a specific blending equation. Let's see if we can find it. I think I saw it on here. Here we go. With straight alpha, blending is symmetric. So a times x plus b times 1 minus x. So pre-multiplied looks like this, which is a times b 1 minus x, which makes sense to what we did. If we look at the function that we're using here, we're adding the two together. So our source color is 1, which is A over here. And then our 1 minus source alpha is this over here. 1 minus source alpha. Make sense? I think it does. Versus, source alpha x 1 minus source alpha. So, cool. Very slick. Yeah, this is a great article. This is fantastic. All right, so that I think is the right way to do transparency. That took a lot less time than I thought. All right, so let's move on to the next thing I wanted to do today, which was uniforms. And, I might roll these two together where we want to do like orthographic projection. So one thing that can be useful when you're working in a game or you're working in graphics is to not need to use clip space. So what is clip space? Let's take a look at that diagram of clip space here. Here we are. So clip space is well and good for shaders, but for us, we might want to work in pixels. So like you might want to work, like say you have, you say you want to have a resolution of 600 by 800 or whatever, you want to work in that. So you might want to transform the space that you work in to be in like pixel space or another space that you're interested in. You might have a different coordinate system that you want to work in. You might want to work in 3D. So you want to work in 3D space, and then, when you want to render it to the screen, we'll use a matrix to transform it into clip space. So that's kind of where matrices come in, where we can transform our coordinates into clip space from whatever coordinate system we want to work in. And that matrix is going to be the same for every vertice on the screen. So that's a uniform. So that's an example of where you might want to use a uniform. So let's take a look. Or, it could also be a constant. Like, you might have some fun stuff that you're doing on the GPU, like some physics simulation. It might be a physical quantity or whatever. And that might be another instance where you might want to use a uniform. So let's take a look at uniforms. All right, let's see here. Let's back up. Let's look at uniforms here. How do we make a uniform? So let's take a look. They're doing some struct here. I don't really care about this struct, but we passed uniforms through binding groups. Okay, so I'm gonna duplicate this tab here real quick, and we're gonna talk about that diagram again and the fundamentals, because that diagram is really good. So uniforms go through a bind group. So to refresh your memory, that's where we put our textures, and that's where we put our samplers. So let's go look at that in the code here. That would be in our bind group here. Here it is, our bind group. So we have bind group 0, and then we have two things on here. We have a sampler and a texture. And so we could, in theory, throw on another binding in here for a matrix, an orthographic projection matrix, or another value. Let's see what the details are about that. Okay, so there's group and binding. We do our thing. Don't really care about this. I want to do a matrix. Uniform buffer. So we got to create a uniform buffer. to assign our data. So let's do that. Let's create a uniform buffer, and then we're going to have to put in our matrix. Okay. This one's a little interesting because this one is really looks like a straight buffer, and then we have to, you know, chunk our buffer into, like, in their example here, they have a struct that has 4 floats, 2 floats, 2 floats. So a vec4 float, and then scale is xy, offset is xy. So we have to pack this uniform buffer. So we have 4 floats, 4 bytes, 2 floats, xy, 4 bytes, 2 floats, 4 bytes. And that's the size of our uniform buffer. And then we have to give it usage. And then we can set values on that buffer. Buffer, uniform buffer. We have to write stuff into the buffer too. Okay, that's where we do it. We don't want to make the mistake that I made that one last time, where you forget to write stuff into your buffer. So you're going to want to remember that. Write stuff into your buffer when you create it. So, okay, let's give that a shot. Let's switch over to the code and create our buffer. Our code is getting kind of messy. We might need to refactor it here soon because it's how long is this file? We're getting kind of long. Well, I'm just, you know, we'll stick it next to the other buffers. You know, why not? It's the, you know, let's keep all the buffers together. They're nice and happy. We'll add it at the top. Uniform buffer. We'll call this a, I'm going to call it matrix buffer because that's what I want. So matrix buffer, we're going to need a device. We're going to create the buffer. I kind of like how there's only one command for creating buffers, and it's called create buffer. So I want a 4x4 matrix. So I need 16 floats. Right? Yeah. So I need 16 floats. Not a vec4. I need 4 of them. Okay. Yeah. So I need 4 bytes. I need 4 32-byte chunks by 4. Okay. So I think that's right. Well, we'll find out. I'm probably wrong, but we'll find out if that's right or wrong. Usage, GPU buffer usage needs to be uniform buffer. GPU buffer usage, copy destination. And it needs to be copy destination because we want to copy into it. So we're going to need to write to the buffer some values. So device q, write buffer. We got our matrix buffer here. And then offset, we're not doing any offset magic. And then we're going to write some data as a matrix. So we need to figure out what the right shape of an orthographic matrix is. So let's go figure that out. Browser. WebGL orthographic projection matrix. Sure, we'll start there. Hey, it's WebGL. It's super useful. Let's see. I really need the formula for orthographic. This is perfect. I'm going to steal this function. So let's grab the formula for orthographic matrix. We can actually look at this on Wikipedia if you want. The orthographic projection, and we'll have a formula here for this matrix. So yeah, so here's the orthographic projection matrix, and here's the inverse of the orthographic projection matrix. And I just wanted code I could steal. So here we go. Orthographic projection matrix. Grabbing it. All right, so we'll grab that code. We'll hop back over to our code window here, and we'll make a function, which is, I'm just going to call it ortho, and we'll paste in our stolen code. Cool. So we have a orthographic function here, and these need to meet number types. So let's do that. Number, number. For near and far, we don't really care because we're doing 2D right now. So we don't really care what the near and far are. As long as they are not like degenerate values, I think we'll be okay. Cool. So we just need to pick, we just need to use this to generate our orthographic matrix. So we can just throw that sucker in here, ortho. So we need the left side of it. I'm going to go steal some values here for this. Let's go look at how we define our width and height here. So we have, in this example, they're using the width and height. Okay, so they're just doing the width and height of the canvas. So we can do the same. I think that makes sense. So we've got our left is 0, so we'll do left, right is 0. Our bottom is the height of the canvas. So let's grab the canvas and client width. Client height is what I want for bottom, client height. And then top. What did I do? This is right. Oh, I had this in the wrong order. What am I doing here? Left is 0. Right, I want canvas client width. So this is left, right, left, right, bottom, top is 0, near, far. Okay, so I think that's an orthographic matrix. I'm just gonna write that out real quick. We'll just show what that looks like. Let's just grab this into a, let's actually stash this into a variable real quick. Ortho matrix. And then we'll write that. Write that to the buffer. Okay, now we're good. Let's go take a look at that over here in the browser. Oh, I broke something. Write buffer failed. Ooh. What did I miss here? Failed to execute write buffer and GPU queue overload resolution failed. Huh, it doesn't know what it is. Oh, you know what the problem is? It's probably because I need to give it a typed array. I bet you that's what the problem is. Dollars to donuts, that is the problem. So let's go over here. to... Yes, I think that's it. So looking at the WebGPU documentation, or the WebGPU fundamentals site, they use a typed array. So I need a typed array. And I really need a typed array of, let's comment this out. I really need a typed array of 16 values, because let's see if that, I'm almost positive that's not what we're returning here, right? Oh no, maybe it is. This looks like maybe 16. Yeah, it is 16. Well, that's great. That's exactly what we need. So let's go ahead and wrap that in a typed array. I'm just going to make this a float 32 array. Just make it return a typed array, because that's always what I want. Okay. Cool. And then we can write that to the buffer, and then that works just fine. So we don't, there's no problems. So, okay. So we've got our orthographic matrix figured out. You know what I probably should have explained is orthographic is like what orthographic projection is versus different types of projection. So if you're doing like perspective, you know, that would be like what your traditional 3D game is. Orthographic is like flat. So if you're doing like a 2D thing, like a 2D game, orthographic projection is kind of what you want. Or if you're doing like an isometric game, you might pick orthographic. You know, you could do, you know, this, you know, or isometric just means that the amount of percentage of like all the angles. So basically it's just a camera position at that point. Yeah, and then if you wanted like a perspective matrix, this would just be different. So we can actually look at what that would look like. Wikipedia perspective. Let's see if they have the matrix in here. Dang it, they don't. Well, they probably do, but it's classic Wikipedia. Yeah, let's see, perspective. Let's see if we got a projection matrix. Nope. There's another formula for that too. So like, you know, like how we have orthographic here, there's a similar formula here for perspective. And we could put that in there, and that would give you like kind of a traditional 3D look. Okay, so next on our uniform journey is going to be uploading that to a bind group. I'm gonna get rid of this console log. So our bind group here, I think I can just reuse our bind group, can't I? Or do I need a different group for the vertex? That's a good question. So I think I'm just gonna try maybe the simplest thing that could possibly work and throw in a group 0 binding 2. I can foresee this being a problem, maybe like if it's out of order. And I want a matrix. So I want matrix, and I want some data type here. What data type? Let's find out. It's going to be like a matrix data type. This were, if this were WebGL, it would be like a mat4. But what do I want here? I want a matrix. Let's say, what if I resource types. I saw it in there. Here we go. So I want a mat 4 by 4. That's what I want. I want a mat 4 by 4. That makes it nice. 4 by 4 float 32. So that's what I want, right? Mat 4 by 4, 32. Okay, cool. That makes it easy. Okay, so we have a mat 4 by 4 float 32 here. Let's see if we can add that to our bind group. The simplest possible thing that could work. So it's binding to, and it's a resource. It's a, is it a resource or is it something else? Let's try a resource. Can I just do uniform or matrix buffer? Does that work? No. Let's see. Let's see what we can do here. Does it just need a comma? No. All right. Follow the types. When in doubt, look at the types. Bind group entry. That's what we're looking. We have a binding resource. Okay, what kind of resources can we do? We can do all of these. We want a buffer binding. So what does a buffer binding look like? So it's an object with a key that is buffer. Okay, so we just need to wrap this in an object called buffer. Neat. Okay. Does that work? No. Okay, let's look at the error. Ooh. Module scope var declarations that are not part of a texture or sampler types must provide an address space. What does that mean? That is a new error. Well, let's take a look at what they do here for this other struct type. So they do a struct, do a var uniform, our struct. Do I need to do that? I don't understand that. If that is what I need to do. Var uniform. Let's try that out. Let's see what happens. So I added a var angle brackets uniform. Okay, I got a different one. Number of entries 3 did not match the number of entries 2 in bind layout. We had expected layout, binding 0, sampler, binding 1, fragment, texture. Is this because I'm not using it? And it's just getting kicked out? It could be the case that I'm just not using it. So if I'm not using it, it's not being included in the compilation. I wonder if that's it. So I wonder if that's it. I'm gonna see, I'm gonna make sure I'm not missing anything here. That seems like we got it right. I don't understand, so here's the thing I don't understand yet, is why I would use more than one bind group. Would I always use more than one, like why would I use more than one bind group in a shader? If I can just like add numbers to bindings. Like why do I need to do a different bind group number? That doesn't make sense to me. Well, let's try using it. Let's multiply our vertices by that matrix and see what happens. So we have our position here, and then we have our matrix. Theoretically, I can just multiply our matrix by our position, and that'll get us a new output position. And that should get us coordinates in our orthographic space mapped to where they need to be in position. I think that's the case. Let me check how I do it in Excalibur here real quick. We can do that together because I don't quite remember. In the graphics context, in the image renderer for WebGL2, how do we do this? Yeah, we take our projection matrix and multiply it by our coordinate, and that's our position. Okay. Let's save that and see what happens. So I added the matrix here. We have that as a uniform. Let's see, does this... Okay, so no errors, but also nothing on the screen. And I think I know why that is, because now we are drawing in a different coordinate space. And in our different coordinate space, so there's nothing on the screen here. It's just red. I'm going to change this back to gray because that's going to be really rough to look at. In our coordinate space that we're drawing here, we are drawing a quad that is 1 pixel by 1 pixel at 0, 0. So let's try drawing a quad at 100, 100, and making it 100 wide by 100 tall. Let's take a look at that. Look at that. We've got things in pixel space now. And theoretically, this canvas is how big? This is a 600 width by 400 high. So let's go ahead and do this 0. Let's do 600 width by 400. And we fill the canvas. Very cool. So now we're in pixel space. So this is probably a more convenient space for us to be in. And I'm going to zip this back to where it was at 100, 100, and 100 high. This is like a more convenient space to work in if you're making a game, my opinion. Because we can do whatever we need to do in like relation to like human pixels, and then this matrix will go ahead and bring that into clip space for us, so we don't have to think about things in clip space. Now, one thing you might have noticed is the sword is now upside down compared to where it was here, where it's right side up. And I think this is because our orthographic matrix now inverted our y-axis for us. So because we're now doing things like our near and far, our top and bottom are, our left, our top and bottom are flipped instead of having the, like, let's take a look at clip space, how clip space works. Let me back up here. Actually, let's go over here. Go back to the clip space diagram. So in clip space, positive y is up, and then in our matrix space, positive y is down. So that's what happened here. So we flipped y, and then we need to flip y again, because of the because we've changed the coordinate space on ourselves. So I will just flip y. I'll just say it's false now. Place. I meant false. So if we take a look at that, our sword's back where we want it to be. And that is because our projection matrix flipped the y-axis on us. So that's why it flipped. Versus like if we were working in an opposite space where we had positive y being up, then that wouldn't have been, then we would have had to flip y. Then we wouldn't have had to flip y because of the image, but there you go. Cool. So let's see what else I've got here on my to-dos here for WebGL. Okay, so we're actually kicking along a lot faster than I thought we're going to. We got our uniforms in, so why don't we figure out animation? So I think animation would be a really good place to go with this, and then maybe a good place to end. Since we've got why do we need to flip the y? We figured out transparency, and then we kind of nailed uniforms and orthographic projections in one fell swoop there. So let's do animation next. So this isn't really WebGPU, but this is just how you do animation in the browser. So I might refactor this. Let's see. Should I refactor it? Maybe not. We'll keep it messy here for now, but then maybe at the end, if we have time, we'll refactor it. Okay, so let's figure out what we need to do to render this every frame. So we don't need to redefine our pipeline every frame. Our pipeline is one and done. We don't need to define our sampler every frame. I think that's good. Our bind group doesn't change every frame. And our matrix, our uniform, you could change a uniform every frame if you wanted, but we don't need to. We have our command encoder that defines our render pass. So we don't think we need to do that. The only thing we need to do is, well, maybe we do need to do the render pass because we need to tell it what pipeline we're going to use. Okay, so maybe we do need to do a render pass every frame. So we need to create a render pass, set all of our state on that object, and then submit that to the encoder. So let's do that. So, or submit that to the device. So let's go ahead and I'm just going to put this in a function called render, or maybe I'll call it draw. So we'll put all this into draw. I gotta screw this up. Device possibly undefined. Okay, let me undo this. So we have draw. It doesn't like my device in my scope here. Okay, I'm just gonna say it definitely is there. Or maybe I should just do the safe. I'll do the, it's definitely there. Cool. So, and for now, I'm just gonna draw, and everything's still working. So we're still drawing our sword to the screen here. We have just moved all of this, like this drawing bit into a function where we can just call it. Okay, so now what we want to do is we want to draw every frame. Uh, so there's a really slick built-in browser function for this. It's called request animation frame. So what you can do is you can call request animation frame. You give it a callback that you want to schedule like the next draw on vsync, and it'll do it. So this will start running the draw loop, nonstop. Yeah, so there we go. Let's go ahead and look at that here in the browser. So that should be running now every frame. So I should be executing draw every frame. So if I set a breakpoint there, you'll notice that I am drawing that every frame. And you can get really fancy with this. You can do the timing, and we might get to that in a second, but you can do time-based movement, so you can know how long between frames that you were, so that you can interpolate movement for characters in your game. So that's one thing we can do in a little bit here. I just want to get it so that we're moving the sword across the screen here. So we've got that working. So now we need to update our geometry every frame, so that as the geometry is updated, so like we're starting at 100 here, we want to update our geometry every frame so that it is moving across the screen. So what we'll need to do then is every frame we'll need to write to the vertex buffer with the new geometry, and then we'll need to draw it. So we're going to need to do some, I'm going to call this, instead of draw, I'm going to call this like main loop. And then I'm going to make a function called update, which is going to update, us. Keeps wanting to autocomplete. I'm going to make a function called update. Just going to update geometry and stuff every frame, and then I'll make one called draw, which is responsible for calling all the draw commands. So, and then I'm going to move the draw commands in there. Cool. So now we've tidied up our main loop. So, and this is actually kind of a common way to do it. Right now we're just looking at the sequencing logic. So like we're like, okay, we start the main loop, and we schedule ourselves again for another call. We're gonna go update our game state, and then we're gonna draw it. Make sense? Makes sense to me. Cool. So let's go ahead and try to update our vertices. So we have a vertex buffer up here. Let's make a variable here for x position. Let's call it sword x. We'll start sword at 0, and then sword y we'll start at 100 maybe. And then what we'll want to do is we'll want to create the geometry, and we'll want to create the geometry here, create the buffer here, but we're going to want to write to the buffer in our update. So I'm going to move this into our update function. So every update we're going to write to the buffer, and I'm going to tell TypeScript that I know that the device exists. And 100. I'm going to let vertices equal. So we got sword x, sword y. That's width and height are going to be 100. And then every frame, I'm just going to, we'll just increment it 1 pixel to the right. So, and then we'll figure out the motion So you can take a look here at the browser. That's for what the sword's doing. So we can go ahead and do sword X. We'll just do 1 pixel to the right. Every frame. So this is kind of problematic because if you have a slower frame rate, then your sword will move slower on versus someone who's got a faster frame rate. So that's typically not what you do, but just to get it going here, we're going to do it this way. And then we'll do the time-based movement interpolated. Okay, so we have sword X, and we're going to update our vertices by creating a quad at sword X. Sword Y, and then we're just going to keep it at 100 height. So that should animate our sword, and in fact it does. Check that out. I'll just refresh it here so we can see it starting from 0. Look at that. We got something animated. How about that? It's pretty cool. And that is pretty slick for WebGPU. I'm pretty pleased with this. Let's go back to coding. Awesome. Let's do the time-based movement here. And then I'll talk about a few things after that, and I think we might call it a little early today, but that's pretty cool. Like we were able to get transparency, we were able to get explain why we need to flip Y. We got uniforms and orthographic projection working for like a 2D game, and then we're working on animation right now. So pretty cool. We're making good progress. Okay, so let's figure out this animation business. So for this main loop, what we're going to want to do is we're going to want to measure how long each frame takes so that when we update, we can scale our motion by our update so that we don't have that problem we talked about where you have that problem where, like, if you have a faster computer, faster frame rate, things move faster than a slower computer or a slower frame rate. So we want to do that. I think I wrote an article about this in the past. Let's find out. Let's see. Sweet, I did write an article about this. So I wrote about animating. This is with coroutines, but I do have a similar setup here. So we can kind of crib off of this. Request animation frame passes your callback the current time. So we can take advantage of this and use the same kind of formula here to get going. So I'm going to go flip back here and go ahead and do performance set now. And then, and this is like a high precision timestamp. So it's like, you get it. Let's see. Let's look up what performance.now gives you. Now, MDN. High resolution timestamp in milliseconds represents the time elapsed since the origin. So I think that's just since the start of the window. So it's pretty slick. Use it for most timing stuff. But let's go ahead and do that real quick. So we've got our time, which is in milliseconds. We need to calculate the time elapsed since the last frame, which is now minus last time. And I'm just going to do last time equals performance now, which going to do it like that. Last time. Cool. Last time. So that's our elapsed. We're going to pass elapsed in here. I'm going to do elapsed. This is elapsed milliseconds. I like to keep our units on a variable. It helps out a lot. And then when we're done, we're going to go grab our last time. That's going to be whatever now was. Cool. So our update is going to take in our elapsed milliseconds. And then I'm going to make a variable up here called sword velocity x. So I want it to move at 100 pixels per second. That's what this unit's going to be. Pixels per second. So I want to move at 100 pixels per second. So how do we do that? So what I need to do to make that happen is I need to convert this to seconds. So we're in milliseconds, so we'll convert that to seconds. There's 1,000 milliseconds in a second. And then for position, what I would need to do is I need to grab the velocity, multiply it by seconds, and that'll give us position. So if we have a velocity of this, this will be the difference in position between frames that we need to go. And then the position will be whatever that was since the last frame. So I'll just do plus equals here. So our x will move scaled pixels per second across the frame. So let's make sure that that's working. And sweet, we've got 100 pixels per second. How about that? It's real good stuff. Let's do like something even faster, just to like maybe prove, or maybe slower to prove to ourselves that it's working. Let's do a really boring value first. Let's do 1 pixel per second. Oh yeah. That's a snail speed. Let's do 1,000 pixels per second. Yeah, it just zips right off the screen. So 100 is kind of a good middle ground there. So that's 100 pixels per second. Slick. We're making really good progress here. Let's take a look at if there's anything in here that I wanted to cover or learn about with WebGPU. Honestly, I think I've got most of the drawing APIs that I was interested in for WebGPU, and the rest is just kind of math. If you want to do 3D, that's perspective projection, like honest to goodness 3D. But the rest of it's like matrix math. So that's pretty cool. That wasn't too bad. I think the thing that is like the most jarring to me is WebGL, the new shading language. I think that's the most jarring because it's a kind of a different syntax here than I'm used to. So I keep wanting to do things like GLSL style. But I think it's, on the flip side, I think it's a good thing because it's very, very clear about where things are coming from. Like you have this built-in where you can, any built-in decorators you can call from the ether. You can say where in your attribute things are coming from. Or where things are going. So like this location can be like an input or an output. So you have your input on your attribute, and then you have your output here as well. The same with the binding. The thing that I don't understand is why you might have a different binding group. Like why don't you just have one binding group? That would be really interesting to learn. But yeah, that's pretty cool. So, all right. So before we wrap up, I might talk about here, but why don't I commit this stuff here? And I'll share the repo with everyone. Let me grab that repository. And I want to talk about like the kind of refactorings I would do next. And maybe we can do some of them. All right, here's the code. So, all right. And if there's any questions from the chat, go ahead and, feel free to let me know. But here's a few things that I might do next to refactor this. I think I would perhaps extract some of the canvas business, maybe all of this canvas business, to a screen type to hold on to all of the screen related logic. I might extract this texture loading to a helper, like a texture service or a texture provider where you can feed it images and it can suck them in. I might make the like a quad type perhaps, or even like if you're familiar with Unity or other game engines, you might make like a game object or an entity to handle that. I might move that UV into there, like into, maybe make a material type. But yeah, I think that's what I would wind up doing. I might refactor this just by moving things closer together. UV by UV. And I might move the shader code into potentially a renderer. I might move that into a renderer. I do like the things that I like about WebGPU is just the fact that you have these really like slick top level types. Like you got a pipeline that defines your the whole pipeline for shaders, which makes it really slick when you're defining these things. And then you have a like render pass where you can have this this object that contains all the state that you want in a particular render pass. I do like it a lot. Yeah. So let's do a little bit of refactoring maybe. Let's put our money where our mouth is. Let's make a screen type. So I want, when I make a screen, what do I want? I want a width and a height. I want width and height. So when I make a screen, that's what I want. So let's go ahead and grab, let's see, I'm gonna do adapter, device, we're gonna make our canvas, our context, we're gonna configure our context. Yeah, we're gonna start with that. We're doing a lot of stuff in the constructor here. And first problem, can't have async constructors. So we're gonna have an init async. All right, so this will go ahead and configure our context. Hey, well, thanks, Chris, for listening. That's awesome. Yeah, that's great. Yeah, it's a learning journey for me with WebGPU. It's definitely been real cool to learn. It's definitely making me excited because like now I'm thinking of places I'm like, oh, I'm just gonna tear stuff out because this will be like way better like way more maintainable. As soon as we get it like to a a higher supported list on WebGPU other than Chrome, this graph has got to be a little more green, but it's definitely something where I'm like, oh, I think I want to make a renderer for this soon, just because it's just so nice to be able to use. Yeah. Thanks for the nice words. I appreciate it. Yeah, check out Excalibur. For folks on the call that haven't seen Excalibur, go check it out. We make fun games. I think we make it hopefully easy to do, at least for my brain. If other things are easier for you and different stuff, go use that. That's okay. I'll be okay. All right, so we got a screen with the width and height. So I want the width and height to influence my canvas. So let's go ahead and do this dot width, this dot height. I'm gonna need the device out of this for later. So we need a device. So I'm going to need to be able to get the device off the screen. And I'm going to need to get the context off the screen. GPU device, public context. I'm going to need the context. GPU canvas context. All right, so there's our two. Let's go ahead and set those. What don't you like? Oh. I'm going to do the thing you're not supposed to do. This wants it to be a context, I promise. Let's see, what is the context that comes out of this? GPU canvas context. Canvas context. Cool. All right, so that's a screen, I think. I think that gets us a screen. One thing we might want to throw on there is the orthographic. Now that I'm thinking about it, I might want to throw on the orthographic projection on there. I might, because that's the width and height of the canvas. I might throw that on there too. And that I can just calculate in the constructor. So we need to do ortho, yoink. And we need to, yeah, we just need ortho. Cool. There's ortho. And then we wanted to do this. With new width and height here. I don't think I need client width and height. I'm going to make this matrix. Okay. All right, so let's make sure that we refactor that and it works. So I'm going to go ahead and do screen equals new screen. And we're going to call it, what was the size that I was using before? 600 by 400. 600 by 400. Cool. And then we need to actually import that. And then let's see, we want to get rid of all of this. And this. And I'm just gonna grab the device out of screen. And then we need to write our screen matrix. Oh, and I broke it. Cannot read properties. Oh, okay. I still have some stuff broken. Okay, so we have the presentation format that I needed to grab out of the screen. So that's another thing we need. There's a lot of stuff here that we need. Pull the presentation format and promise that it'll be there. And then what are you complaining about? String is not assignable to GPU text format. Oh, yeah, GPU texture format. There we go. And then we'll go back here, and then we need screen dot that. And then what else is not happy? 29 is not happy. I think we need to actually call init separately because I need to know when this asyncness is done. Yeah, so we need to await the init. Cool. All right, so that should do it. We need screen here, and we have another error over here. One of my nested. Here we go. All right, cool. We refactored it. It's took a little more than a little more doing, but it's now working. All right, cool. So now we have our uniform buffer and our texture. What do we want to do next? I want to do, let's do textures, because that seems like a thing we can make happen. So let's make another helper, and I might just call it texture for lack of a better name. And I really just want an image path that we're going to load. And then I'll just make a async load. So when we create an image, we need an image path. We're going to decode it. And then we're going to go ahead and create a texture on the device. So this is interesting. We're going to need to have a device. I really don't like having to pass a device in here. Maybe we do it on the load. Is that any better? We'll find out. All right, so we're going to load a texture. Oh, and you know, maybe we just need the screen. Screen is doing a lot of heavy lifting for us, so it makes me feel like I want to refactor it. We'll keep it for now, but I'm a little nervous about us using a screen everywhere. Makes me want to be able to inject like the device potentially. Okay, well, we'll go with this for now, and then we'll work out the kinks just to chunk out some of this. So we got our image and our sword texture here. So when we load, what we're going to need to do is we're going to need an access to the texture itself, the actual GPU texture. I'm just going to call text GPU texture. So this is going to be the actual texture that we're going to use later. We're going to load it. So we're going to create it here, and we're going to go ahead and load it with our bitmap. And then we should be good to go. I don't have any more swords in here, do I? Okay, good. So I can go ahead and do this. Actually, I want to do, okay, so I want to do a new texture. I'm going to call it sword texture still. I might just call it sword. Yeah, no, I'll call it sword texture. New texture. And then we got our sword PNG path that we're loading here. We want to import that. And then that should be it. I can get rid of all of this code probably. And then I need to update this to be text. And I think that's it. No, I got an error over here. 164. What doesn't it like? Undefined. Oh, you know what I didn't do? Is I didn't load it. So I created a texture and didn't load it. There we go. Sword texture is now loaded. All right, we're reducing lines here. Okay, what's next? We've got UV coordinates. We've got a quad. And a vertex buffer. Okay, what I think I want to do is maybe make a simple data structure kind of similar to how like some other game engines do stuff where they have like a sprite, and then, you know, that's just a quad that you can move around. Let's do that. Let's make a sprite. And then you can give it texture, and then you can move it around. So export class sprite. We're going to have an X position, a Y position. We're going to have a X velocity. Let's see. I'm going to call it velocity X. to start at 0. 0 for everything. Velocity line. We're going to give it, I'm just going to give it a texture, our texture that we invented. We're going to need, what else are we going to need? We're going to grab this create quad function. It's not clip space anymore. So we'll create a quad every time we need to draw it. Yeah, and then we'll keep track of the UV coordinates. Those don't change. So that can just be constant. You know, honestly, we can just have like a public UV hanging off of this thing. And then I guess we can have a public geometry. Why not? We'll have it so that you can mess with the quad if you want. Sure, we'll make it at 0, 0. This dot x. This dot x. Oh, you know what? Let's give them a width and a height. Oh, you know what? Yeah, let's give it a width and height. Sure, they're 100 by 100 by default. Cool. So we got a quad. We got UV. We got a texture. What else do we need here? So we got velocity, quad UV. Got a vertex buffer that we're uploading. The shader is kind of part of the renderer, so we don't need that. We could maybe pull a shader into a material type. But maybe we're going too far. I think this might be the last refactoring. So I think what I'll do is I'll finish this sprite thing up and then I'll talk about where I'd go next. But I think this is a good stopping point after that. Cool. Let's go ahead and make that change. So we got our UV buffer here. Honestly, the UV buffer didn't change either. Okay. So let's add a draw to this. And when you draw, you're going to upload to GPU. So that's when we're going to fill any buffers that we need. Oh, I need to actually import the screen. Okay, so in here, we're going to upload our, let's see, we have our vertex buffer here. And every time we draw, we're going to upload our vertex buffer. really, I want to, I don't know if I want to do this. I don't want to have a device in here. Let's see. What I would really like to be able to do is not have to think about this stuff. I would like, but maybe I need to because this is actually what's doing the drawing. I actually need to do this to do the drawing. This draws the whole frame, not just one thing. Yeah, so I think I would need to add a vertex buffer. Okay, here's what I think I'd need to do. I'd either need to encode everything I'm drawing into one vertex buffer, so like doing like batch drawing, and then draw everything at once. Or draw individual items as different draw commands. So drawing on top of the previous frame. So doing multiple draw calls. So doing multiple draw calls, each draw call drawing one thing at a time. In that case, would I want to clear the screen? I think I'd want to do something different. So I wouldn't want to clear the screen in between draws in that case. Okay, so I think what I'm going to do is, that's getting complicated. So I'm just going to make it so this quad updates its geometry. So we're going to update our position. Every frame. X, Y, this dot width, this dot height. This is a number. We'll make the width and height the same as the texture. Okay. Cool. So we got that cooking. Let's go ahead and replace that stuff with what we got. New sprite. And then sprite has a velocity x of 100. That's pixels per second. And then we don't need geometry or UV. So we have a UV buffer. And our UV buffer is always going to be a quad. So was it sprite? Byte length. I'm just going to do this for now, but this is not what I would normally do. And then we need sprite, update, lapsed. And then do that. And oh, my parcel died. Let's restart that. Let's grab that. And let's take a look. It's working. We refactored it. All right, I'm gonna do just a few more here because this is kind of funky, these UV buffers and vertex buffers. So how big is our UV buffer in byte length? Sprite UV, because we can share the UV buffer. Byte length. So that's 48. Because, okay, so 48, let's see. So that's 6 vertices times 32-bit times, that's 24. Why is it 48? Let me look at the UV that we generate in Sprite. 6 vertices. Oh, but there's 2 coordinates per vertice. That makes sense. Okay. So 6 vertices. There are 4-bit. There are 6 vertices that have 2 components each, and they're all 4 bytes. And then that's the same story for quads. We want to do this when we draw, just in case we want to animate UVs. So I'll move this back down. We're going to fill our vertex and UV buffers at the same time. Oh, I switched away from coding. So I just moved this this down. So we're writing our buffers at the same time after we do our sprite updates. And then we're drawing. Cool. I think we're getting closer because we're creating the buffers. We're creating the buffers once since we can share. Now the trick is, can we do 2 sprites? Can I draw 2 sprites at once? The answer is probably no. Make sprite 2 start at the other side of the screen. sprite 2. We're going to update. Lapse milliseconds. And then we'll need to figure something out for this. So I want to fill the buffer. Maybe I want to fill these buffers in between draw calls. So I want to like fill the buffer, draw, fill the buffer, draw. So for each sprite, okay, let's try that. Let's try that. So I'll make a list of sprites. So we'll have a list of sprites, and then we will loop through them here. For let sprite of sprites sprite.update elapsed milliseconds. And then what we'll do here is this is going to be filling the buffers is going to be part of drawing. So what I'll wind up doing here is I'm going to do this whole pass for each sprite, which I don't think is necessarily right, but we're going to start there. For each sprite, we're going to draw, and then for each sprite, we're actually going to fill the buffer. Okay, so interesting development. One of them is working, and it's the last one, because I bet you it's because we're clearing the screen in between. So let's refresh that. So yeah. So I don't want to clear the screen. How do I not clear the screen? There's this color attachment. And we have a clear value, begin render pass, load op, store op. Well, let's try not clearing the screen. So we have load or clear. So let's just try load. Oh, that's interesting. Oh, that is super interesting, because that's like we don't have our clear color. So it's just completely transparent. Well, that's working. How do we get our clear color back? So we got two things working at once. That's pretty cool. Let's look at some examples, I guess. Excuse me. Let's see if the importing images gives us any help. Render pass. Do we need like another render pass to do the clear color? Well, I'm going to give it a college try here for another few minutes. I think if I don't figure it out, I think we're going to leave it as a mystery. But I am fairly pleased in that we have multiple things rendering at once. So that I think is a victory. Let's see. Let's see. Well, let's see what basic WebGPU rendering looks very similar to what we were doing. They're doing some WGL render pipeline, store op, load op. Oh, what happens if you don't specify a load op? Oh, you need to. You must specify a store op in the color attachments. It's recommended to prefer clearing. I wonder, okay, let me try something real quick. I wonder if I make a like a render pass here that is just a clear color. Let's try that. What if I do const clear pass equals command encoder begin render pass label clear color attachment. We're just going to do the same thing here, except it does nothing. Why is this complaining? Okay, I must have had a typo there. So we're gonna clear, and then we'll, yeah, we're gonna clear, and that's it. So the clear pass is gonna go clear pass. It's got nothing in it. It's got no pipeline, and it's just gonna end. Let's try that. Well, not quite. That did not work. Oh, you know why it didn't work? It's because I did it in between the sprites. That's why it didn't work. So if I move the command encoder outside the loop and I clear before, does that help? It doesn't. You know, okay, let me submit after I'm done. That still doesn't help. Huh. So, okay, so here's what I got right now. College try. I've got a clear pass that just does a clear on the screen. And then I have two passes for, I run a pass for each sprite, and then I submit all the commands to the device. I would have expected this to work. Can I not specify a clear value here? No, that still doesn't work. Do I need to draw my clear pass? Oh yeah, it does not like that. Yeah, very confusing. I would have expected that to work. because I'm doing a cleared render pass. I'm doing a load and a store. Maybe it's compositing on the store. What options do I have on the store op? Store discard. Probably want store. Well, that is a mystery. Let's see. I want to draw multiple pass drawing. Not multiple pass, but multiple WebGPU pass. Yeah, I feel like in the naive case, if you don't want to build a batch renderer, like you need to be able to do this, right? This feels like the right way to do it if you're doing like a naive like multiple, even if you're not doing a naive thing, like you're doing a render per material, like you want to run passes on top of each other. How do you run multiple passes? Let's see. You know you're in trouble when you're on Reddit. Yeah, I might be stumped. Well, that might be a project for next time. If I go ahead and get rid of this clear pass, I think things just work. So let's go take a look. I could have swore I had it working without the clear pass. Was it not ever working? Wait, when was this working? I'm losing my mind. Interesting. Okay, it was... Okay, hold on. Interesting. I think I've got an interesting nugget. So if I submit one final command encoder finish, it doesn't work. But if I do two inside the loop, oop. Oh, hello. Error recording command. That's new. Oh, but in the old one, here's what I was doing. I was making a new command encoder for each. And when I do that, it works. I was doing command encoder, begin render pass. That's interesting to me. Command encoder. Why would that be the case? That doesn't make sense to me. Let's go look at the WebGPU command encoder. All right, let me just look at command encoder. Command encoder. Initialization steps. Command encoder. Coding command to clear a buffer. Finish. Command encoder finish. I feel like I should be able to do multiple passes here, and I'm just not understanding what I'm doing wrong. Like, I should be able to write multiple passes. Unless I'm misunderstanding what pass means, which is very possible. Pass encoding. Begin encoding a render pass described by the descriptor. Begin compute pass. Begin. We're not doing compute. Well, I am very confused. Finalization. Once finish has been called on the command encoder, it can no longer be used. Makes sense to me. I wonder if I did... Okay, let me try this again. Let's see. Let's move... So we were doing a command encoder for each inside the loop here. But if I move it out, then it doesn't work. That doesn't work, obviously. If we do a clear pass, that does not work either. It's like the first one doesn't get drawn. Is it... Hold on. Hold the phone. Is it because I'm trying to reuse the vertex buffer? And that... Okay, I think that might be what's going on. Right? Because I'm trying to reuse the vertex buffer in the same pass. I think that might be it. Because... Okay, I think that might be it. Because if I make them different passes, then it works. I bet you it's because this vertex buffer, because I'm changing it in the pass, it's messing with it. I'm almost positive that's what it is. I bet you that's what it is. So I wonder if I made... Let me make a vertex buffer for each sprite and see what happens then real quick, because I'm dying to know. So let's make a vertex buffer for each sprite. And then I bet you that'll work. I bet you it's because I'm blowing away the thing, because like the reason I think that is because my clear pass is working, because I have a clear pass here, and then my other pass is like if my two passes are not working here, or they technically are, it's just drawing on top of each other because they're sharing the same vertex buffer. That's 100% what I think is happening. Yes, I think that's what's happening. So we can fix this. So I'm gonna do a bad thing, and we're gonna create a vertex buffer. Actually, I'm just gonna pass in the device or the screen here to the sprite. And then we'll just grab the device off of it and make a vertex buffer that way. And then we can yank the vertex buffer off and do that. I bet you that's what it is. I am so confident right now. If it's not that, I'll be really sad. Let's see why. Oh. All right, so vertex buffer. All right, so then we have, I can go back to this dot quad dot byte length. Actually kind of makes some sense. Cannot read device off of undefined. Okay, so then we can get rid of this vertex buffer, and the UV buffer we probably should, okay, it's okay that we're overwriting it because the UV coordinates don't change, but it's definitely, like, they don't change right now, but it's definitely a problem, so we'll have to get that next. So then we do sprite dot vertex buffer. We write into our quads, and then we need sprite dot vertex buffer. Oh, holy moly, that's what it was. Oh yeah, victory. All right, so that's 100% what it was. So now we can have unlimited sprites. Neat. All right, that's what it was. So cool. All right, so that makes sense, I guess. So that is 100% how you would do multiple render passes if you're gonna do, like, if we're gonna do naive drawing, like a draw pass per thing. That makes a lot of sense. Okay, let's fix the UV thing, and then because that's gonna be a booby trap for later. But then I think we're good. UV buffer. Oh, switch back to code. So I'm copying the UV buffer in here, and then we can switch back to this being this.uv. This actually feels good. This feels pretty good. Awesome. And then we can go back in here and we can get rid of this. And then we got to fix this. sprite.uv, sprite. And then we fix this. Huzzah! We got our two swords. Very cool. And now this file is getting a little more readable. We got all our sprites. We're updating all our sprites here. We've got our only material, our only shader and render pipeline here. So we could that maybe that's a thing for another time. But what I want to do is I want to maybe make these sprites go bonkers. Let's make a ton of them. I equals 0, I less than, I don't know, let's start with 100. Let's start with 1,000. Let's go high. And then give a screen. The API needs a little work here, but you know, I'm feeling pretty pleased with how this is feeling so far. You could maybe see how that you could take this and make this into a game. Okay, so let's set some random velocities here and positions. Sprite.x equals math.random times 600. I think we have 600 width, y 400, and then let's make some random velocities. Let's see, we'll do, you know, between 100 and 200 pixels per second. How about that? Actually, you know what? We want negative directions too, don't we? So we want to do, yeah, let's do this. So if we get random, so if we do random between 0 and minus 200, and we add 100, that's not going to get what we want. We want like the other way, other direction, right? No, I don't remember how to do this. Let's see, random and range. My brain is turned off. There we go. That makes sense. I grabbed a random and range from the internet. Let me make sure I understand this math. So we're going to take our maximum minus our minimum. So we want between 100 and minus 200. So that's 200. This is going to handle negative numbers. Our max is 100. Our min is minus 100. Oh, plus our min. I see. So it's 200 minus 1. Okay, so I was close, but my brain is turned off. So we want our minus 100 and 100. Let's do that. Sweet. Nice. Okay. Look at that. We got a lot of swords. Let's do it again for giggles. A 1,000 little swords moving around. Awesome. Well, I think that is a pretty good ending point. I'm pretty pleased with how the code turned out here. Ooh, wrong one. I'm pretty pleased with how the code turned out here. You can probably see how you could take this and run with it. like some optimizations that we could do here are like we could turn this into like a batch renderer where you can do I'll draw all the images in one pass. If you pack all of your draws, like all of your like sprites into one vertex buffer, and then you could just fire them all at once. You could do that. You could refactor this shader module business and pipeline into a material type. So like if you wanted to like have different materials, and a material might take a texture, like a texture and a shader. So you might do that. You might do some fancy pants stuff, like you might want to do like post processing. But yeah, this is looking pretty good. So I'm going to commit that. And we will go ahead and push that up. And I think we might call it there. I don't know if there's any questions, but it turned out okay. I'm pretty pleased with the refactorings. It took me, my brain is slowing down here after the workday. So it took me a little longer than I'd hoped, but we got transparency, we got animation, we did some refactorings. We figured out how not to use vertex buffers, so that's always good. But yeah, thanks, Chris. Yeah, it's looking pretty smooth. I'm fairly pleased. So join me next time. I'm gonna stream about maybe something else. I might do like platforming physics. I might do physics. I don't know. I might do something else that's fun and game related. I might do some Excalibur coding. So if you want to see me struggle while I work on Excalibur, that might also be something I do. But yeah, I think we're gonna call it for today. I appreciate the few folks that were watching, and I'll have this posted up here as a VOD as well, and I might throw this up on the YouTube as well. Anywho, thanks again for watching. Appreciate it, and check me out on GitHub, and any support is awesome. So thanks again.